Good afternoon. We'll go ahead and get started here. I want to start out by welcoming you all to the 2020 Mechanical Engineering Senior Design Conference, the green session in this case. I am very excited and honored and privileged to be able to bring you this host of students here representing green projects, or what I had been able to fit into the green category. We have 3 concurrent sessions, and you're welcome to pop in or pop out as you desire. I am proud of all these teams, and I hope you'll enjoy the program that follows here. We'll be taking a 30-minute break at a certain point here at about 3 o'clock. And then we'll finish the latter round of the presentations after that. And then we'll shut down after the turbine distress simulation tool team presents and allow our judges, who are members of our Industrial Advisory Council, who have kindly agreed to join and help judge and assess and support this program in its continuing effort to sustain our national accreditation. And this senior project conference is a critical part of that effort, and we appreciate those guys being here, ladies and gentlemen of the Industrial Advisory Council. We are going to start out with the crack arrest treatment system team. That's a team of 4 individuals. I'll let them introduce themselves. I'm going to check with them now to see how they're doing. Are you all there, gang?
Yes, sir.
All right, very good. That was Miss Page. And what I'll do is let you guys kind of set up your screen the way you want it. You can play with your control function, left mouse button drag, or whatever type of pointer you want to play with. I'm going to stop sharing and let you go ahead and share. And then you can go ahead and share your slides and start getting ready to present. And I'll let you know when to go, because there's going to be people turning in just in time, and I'll yell go. And so while we're talking about that, it is important that we stay on schedule. So each team is given 20 minutes to present, and there'll be 5 minutes for a question and answer session. And then we'll need to break that off in order to get the next team up and going and making sure everything's set up well for them, that they can point, that they can transmit from one slide to the other in good form. And so we're going to need to really lean on those. So when there's 2 minutes to go, I'll signal such. And when there's 1 minute to go, I'll signal as well. And then I will get the other team on board there, all right? And so that's how we're going to proceed. So I'll make an effort to mute people and backgrounds from different audience members. But if you could mostly police yourselves on that, you have the opportunity to mute both your microphones so we don't hear any background noise from where you're coming in from. And we have and if you could mute your, it's optional, but you can mute your camera as well. That would work fine. And so what we'll do is we'll give Paige an opportunity to throw her presentation up on there. Let us see it, make sure it's visible, and she can start playing with the transitions and the pointers and stuff.
You haven't enabled participant screen sharing, Dr. Cardenas.
Here we go. I'll do that right now.
All right.
Okay.
All right.
Now we have to.
All right, I think we're ready for you whenever you are, Dr. Cardenas.
All right, we'll give it a minute or two here. Make sure. Okay, at this point, I'd like to welcome the crack arrest treatment system team. It is your court and your ball game. You may proceed. Thank you.
Good afternoon. Our project is the crack arrest treatment system sponsored by American Electric Power. I'm Harley Moss.
I'm Jonathan Zidlogic.
I'm Paige Stansbury.
And we're also working with Sam. I think she might be having some microphone problems.
So today we're going to go over our problem statement, project goals, final design, performance evaluations, conclusions, recommendations, and broader impacts. So a little bit about American Electric Power. They're an electric utility provider and they provide power in 11 states. Our sponsor that we have been in contact with throughout the years, Bryce Daniel, and we actually got to visit Bryce at the Perky plant shown in the picture on the left in earlier fall.
I think we're currently missing Sam. Well, I guess to save on time, we'll just kind of keep going. But anyway, the problem that AEP presented us with in the beginning of the school year was that they are dealing with fatigue cracks in their pipes and also hydrogen pitting. So you can see an example of both fatigue cracks and hydrogen pitting on this slide. And these are a problem because they weaken the pipes that are undergoing fatigue loading and in just generally high stress environments. And this can be extremely dangerous as they can be prone to unexpected rupture and failure. And this causes a lot of extra unforeseen costs and downtime when they have to go in and repair this. So they reached out to us to see if we could implement some research to try and address this problem.
Current research is being done at Louisiana Tech under the advising of Dr. Cardenas to investigate the electroplating of the cracks. The general setup that they're using can be seen on the screen. As you can see, the specimen includes a crack. They fill that crack with an electrolyte solution. They stick a titanium electrode in the solution, supply some power to it for a certain amount of time, and these bridges start to form within the crack, which increases the fatigue life of the crack because now the bridges have to fail before the crack can continue to propagate. These are the results that they're seeing, that the graduate students are seeing in this research. So as you can see, the crack growth projection based on Paris's law is graphed as the dotted line, and the diamond-shaped data points are the measurements that were taken during their research. So once the treatment was done on the specimen, for 9,000 cycles, they didn't see any crack propagation. So these are the type of results that we're trying to see in a larger scale application.
So our project goal was to create a crack arrest treatment test system using the research that Dr. Cardenas and his grad students have been doing to help with these fatigue cracks and hydrogen pitting that AEP is experiencing in their boiler system. So in our test system, it's 10 feet long, and there are 2 segments in our piping system that are actual pipe from AEP. And in this picture below, on the left is before electroplating, and on the right is after, and you can see the gray substance on the inside, and that is the iron-based particles that were electroplated. So this is our final design. This is a SolidWorks model. On the left, we have our pipe system supported by the frame, and in between the flanges on the top and bottom section, that is the pipe from AEP. On the right, we have our cart. On the top shelf, it has our volt meter, our power supply, our spool that will house the electrode, and then the pump. On the bottom shelf, we have the tank that will hold the electrolyte solution.
So before getting too much further into the presentation, we just wanted to go over the electroplating process as we're using in our project. So as you can see here, this is a cut or a cross-sectional view of the pipe that was provided by AEP in between the 2 flanges that Harley was describing in the last slide. It's filled with an iron-based electrolyte solution and has a titanium anode running down the middle. So when you hook it up to a power supply, as shown in this picture, the movement of the electrons forces the iron ions that are suspended in the electrolyte to plate the inside of the pipe. And that's going to be what forms that light gray coating that you saw a couple of slides ago, and is going to be what hopefully fills and arrests the fatigue cracks in the pipe. It's also important to understand what corrosion potential is and how we're using it for this project. So here's the same cross-sectional view. And what we do here is we insert a reference electrode, We hook it up to a voltmeter, and then we also hook the pipe up to the same voltmeter. So basically what the corrosion potential is, it's a voltage difference in between the two materials in the system. So in between, in this case, the reference electrode and the carbon steel pipe. And that would give us a certain voltage output on the voltmeter. And then whenever we run our treatment process and the inside of the pipe is plated in a layer of iron, that corrosion potential or the voltage displayed on the voltmeter will change. And that's kind of how we can track the change in the inside material of the pipe and basically just the success of the corrosion or of the electroplating process without having to take apart the pipe or cut into it in order just to see what's going on inside.
Here's the final design for the pipe system and frame. The frame is made of extruded aluminum and holds the pipe system using U-bolts. There were two design options originally for the pipe system, the two-bend system seen on the screen and a four-bend system. The two-bend system was chosen ultimately because of the ability to thread the electrode through the pipe, but other factors such as safety and usability were also taken under consideration. 3 engineering analyses were done on the pipe and the frame. The first one was to size a pump in order to pump the electrolyte solution into the system. Bernoulli's equation was used, adding major losses from height and pipe length and minor losses from valves and fittings. And it was calculated that we needed a pump that would be able to provide 2.5 feet of head. On the next slide, you can see the free body diagrams for the analysis done on the support frame and the U-bolt. For the support frame, the stress and the deflection were calculated. It had a deflection of 0.01 inches and a yield factor of safety of 8.2. And on the U-bolt, the stresses were calculated and it has a yield factor of safety of 4.6.
Another component that we had to consider was the electrode, which included 2 different parts. The first part being the titanium wire, which was going to carry the current through the pipe system. You currently can't see the titanium wire and the electrode assembly pictured on the left because it is surrounded by the orange hose that is pictured. We decided to use that in our assembly because we didn't want the titanium wire to contact the inner pipe walls, because if there was contact, then it would create a short in our circuit, which would stop the current from flowing through the whole section. We also created holes in our hose because we wanted the electrolyte solution to be able to submerge the titanium wire when electroplating was taking place, because if not, then that would be another reason for it not to be successful. The other part of our electrode was the reference electrode that Jonathan talked about earlier. We ended up designing a housing for our reference electrode because on the end, that white part is a ceramic tip and it can be easily damaged, especially if we're threading it in a pipe section. So we created that housing and you can see that whole assembly for our reference electrode in the SolidWorks drawing on the right. This is our final design for our cart system. The main reason for our cart system is to house all of the equipment needed for the electroplating process. So you can see that the cart system includes a pump, a spool that's going to house the electrode that I just described, a tank that's going to store all of the electrolyte solution, and a power supply. In order to choose a power supply, we ended up having to do current calculations, which included multiplying a current density that was provided by the research being done at Louisiana Tech, and that ended up being 2 amps per decimeter square, and we multiplied that by the area that we wanted to plate for our system, and we ended up getting about 20 amps of current for our particular system. So that's why we ended up choosing a welder for our power supply, because we knew that that amount of current fell within the range that the welder could supply. This is our final assembly for our cart system. As you can see, it resembles the SolidWorks drawing on the previous slide very closely, and it includes all of the components that I listed previously. On the picture on the right, in this slide, you can see the power supply circuit diagram. We ended up grounding the pipe and frame assembly with the use of cable lugs that were attached to the flange part of the pipe assembly. And we ended up supplying power to our system with the use of electrical connections to our titanium wire.
Here are the two components of the final design together, along with a top-down view of the top shelf of the cart. As you can see over here with the pipe system in the frame, there are 3D printed flange covers that act as a barrier for the test pieces, and the bend in the system was changed from two 90-degree bends to conduit bends in order for the electrode to thread easier through the system. To give you an idea of how these two components work together, I'm going to go through the steps of the system for the electroplating process in our final design. First, the solution is pumped into the system from the top valve, and once the system is full, the cap on the Y fitting is removed, and the orange electrode that you can see on the spool is inserted into the system, and measurements are taken with the voltmeter in the two sections in between the flanges. Once it is fully inserted, the power supply is turned on with the appropriate current and run for a set amount of time. Then the power supply is turned off and the electrode is pulled out, taking readings with the voltmeter again as it is wound up on the spool.
This is the economic analysis for the total production cost of the cart. It came out to be $1,468. And for an additional 10 feet of pipe to be treated, the materials will cost about $290. In the chart, we have 5 sections: the power supply, the electrode, the solution, cart, and labor. And you can see the components that make up each of those sections with the prices. So for our performance evaluations, we tested the total system and did some benchtop testing. For the total system, we measured the corrosion potential. For the benchtop testing, we still measured corrosion potential with the addition of measuring the mass deposited after the electroplating process.
So the first performance evaluation that we did was just kind of trying to see how does our cart system actually apply this treatment system to a real piping system. So as Sam mentioned a couple of slides ago, we started by inserting or pumping in the electrolyte solution. Then we threaded our electrode through the piping system, taking corrosion potential measurements in the 2 measurement regions that you can see on this figure. Then we ran the treatment and then pulled out the electrodes, taking new corrosion potential measurements along the same locations. So we ran a couple of different tests just to kind of get a good idea of what was going on the inside of the pipes. And here are the results of our changes in corrosion potential for both the upper test section and the lower test section for the 2 different tests that we ran. Basically, what you can see here is that there was a noticeable change in corrosion potential from before to after the treatment for both tests and for both test sections. So what this shows us is that this cart system does work at applying the electroplating to the inside of the pipe in an actual piping system, and it can be expanded further outside of just like a benchtop test or just a laboratory setting.
Because we saw successful plating once treating our total system, we decided to shift our focus to benchtop tests to see what was actually happening when we would plate our electroplate within a cracked piece of pipe. So this is the general setup that we used for our benchtop test. As you can see, we used a benchtop DC power supply to supply a set amount of current with a resulting amount of voltage. And then we used a carbon steel test section that included a cracked piece in it, and those were provided by AEP. These are the steps that we used during our benchtop test. So we first took measurements of mass and corrosion potential, and then we treated our piece of pipe for 10-minute intervals. And between each 10-minute interval, we took measurements of corrosion potential and mass. And we also took pictures of our crack to see what was visually happening between each 10-minute interval. So these are examples of the pictures that we were taking during our benchtop test. So as you can see, after 10 minutes of plating, we saw iron deposition on our surface wall of our pipe, but there wasn't as much deposition within the crack itself. But after 90 minutes of plating, we started to see a substantial amount of deposition fall within our crack.
The first benchtop performance evaluation that was analyzed was a change in corrosion potential. As Paige mentioned earlier, for each time interval, the corrosion potential was measured before and after the plating. The mean change in corrosion potential was found for each time interval with 5 test sections. The results are available here on the screen. You can see from the graph that the biggest change in corrosion potential occurs during the first 10-minute interval. Afterwards, the change in corrosion potential did not change very drastically. After the change in corrosion potential was found, it was compared to the change in mass for the different time intervals in order to see if there was a correlation between the two. The comparison can be seen here in the graph. Similar to corrosion potential, we see the biggest change in mass happening in the first 10-minute interval. Afterwards, we see that the mass of the pipe still changes with every 10-minute interval. There's no significant correlation in the data, so what we can infer from this comparison is that while the change in corrosion potential does show there is plating occurring, it cannot predict the amount of material deposition.
So as Sam just said, we weren't able to actually track what was happening in terms of the mass deposition on the inside of the pipe with the change in corrosion potential because there wasn't any correlation there. So whenever we came across that, we decided to try and maybe predict how much mass would be deposited for every set amount of time. And to do that, we used Faraday's law, which can be seen here. So basically, this is a conversion from the time and the current to the number of iron particles that are involved in the electrical reaction. And from this calculation, we determined that about 0.2 grams of iron would be plated onto the inside of our pipe section for every 10 minutes of treating. We went and plotted that against the actual change in mass values that we were measuring. And with the exception of the first time interval, we saw an extremely good correlation between the predicted values and the actual values. This is an important or an interesting finding because we can now use Faraday's law and the predicted mass to pretty much set up a treatment system to hit certain parameters. So if we have a certain number of cracks and a certain size that we know we want to treat, we can figure out how much mass we think we need to treat those cracks, and then basically size the time and the current needed to hit that sort of parameter.
So from both of these testings, we were able to make some conclusions. For the total system, it was evident that electroplating was occurring. For the benchtop test, like Paige said, looking at the inside of the cracks, it showed that the inside cracks took longer to plate, and then corrosion potential wasn't the best way to determine how much mass was deposited, so the use of Faraday's law was used for that.
So our project focused more on like a macroscopic view of how this lab research could be implemented in a total pipe system. But as AEP continues to decide whether or not this research is applicable or could be used in their power plants, we recommend that they continue to look at maybe a smaller scale view or more microscopic view of what's happening during this treatment system or during these treatment processes. So first, we'd recommend looking a little bit closer on what's actually happening inside the crack whenever the treatment system is applied. We recommend investigating the effect that this treatment has on the strength and fatigue properties of the cracked pipes, and then also investigating the effects and the behavior of the corrosion of the actual electroplated material over time and how that might affect the strength and the fatigue, and also how it might affect the processes in which these pipe systems that we'd be treating are involved.
If this project gets implemented, there are a variety of impacts to consider. First, in terms of safety, fatigue cracks and high pressure and temperature piping systems are very dangerous. The project could drastically reduce the risk of unexpected failure, which would greatly increase the safety of those who work around them. In terms of public welfare, the crack rest treatment project can service a wide variety of industries, including but not limited to power or oil and gas. In terms of economics, when starting to implement this project, there may be a significant upfront cost with implementing the system and building the carts, but the hope would be to lower overall maintenance costs and any costs due to unscheduled downtimes.
So that about wraps up our presentation. If you have any questions, we'd love to hear them.
Okay, and I'm happy with receiving questions via chat. Members of the advisory council, you can just unmute and speak up directly. We'll go with either one of those options, and I'll be looking for all of the above.
Yeah, I guess I'll kick it off. Hopefully you can hear me. This is Justin Bounds.
You sound great, Justin. Thank you.
No, thanks. From the Industrial Advisory Board. First off, good job on the presentation and the project. I know this isn't exactly how y'all were hoping to finish up the project, but one question I do have is, can you explain a little more why you expected that there was a difference between the upper and lower spools in your testing?
In terms of like the upper and lower test sections here and here, with the corrosion potential measurements.
Yes.
Okay, so when we were running these tests, didn't really have any way to understand exactly what was happening on the inside of the pipes in terms of how much this electrolyte solution we could get in there. So there's the possibility of air bubbles somewhere, especially in the bottom section of the piping system, and then just that was pretty much the only real thing that we came up with in terms of why we thought that maybe there wasn't as much, or there was a different amount of plating down there.
Okay, thanks.
Hey guys, this is Matt Wallace. Good job. I think y'all did a really good job, especially virtually. That's kind of disconcerting sometimes. So is there anything as you went through the project and went through the testing that surprised you, or anything that happened that you didn't expect that you had to adjust to?
Sam kind of mentioned earlier in the project, the assembly that we're showing in the picture on the top right, that includes the 90-degree bends, but we ran into a few snags whenever we were trying to thread our electrode through the system because it was struggling with the friction and with buckling. So that was one snag that kind of threw us for a loop. So we had to change to the more curved bends.
I'd also maybe like to add to kind of a separate thing that we found that was interesting was the correlation between Faraday's law and what we were actually seeing on the inside of the pipe. I feel like none of the other stuff really lined up with what we were expecting to see. Like kind of like what Paige had said. We were running into problems all the time, and then we came to this, and it like actually worked. And it was kind of probably one of the things that worked the best for us. So that was interesting and surprising to see that correlation there.
Very good.
All right, other questions? I'm going to check chat here. It looks like I have one. Here's a question from Kyle Sedlasak. How was titanium selected for the Electrode?
I'll take that one. Titanium was being used by the researchers at Louisiana Tech, I guess long before we started working on this project, but probably the main reason that titanium was chosen for their situation and then for our application was just because of how uncorrosive it is, if that makes any sense. So it's very unlikely to corrode in environments like this one, where we're basically forcing the corrosion of, like in this case, the electrolyte, because there is no like real anode in this situation. But if it was made out of something else, like I don't know, copper or any of the less noble metals, if you will, we would have seen a lot more corrosion, which would have could have broken the electrical circuit or left wire inside the piping system, which both would have been bad.
Hey guys, this is Sam with the advisory council. Great job presenting. Anyway, I like the whole setup here. But have you guys received any feedback from American Electric Power? And I'd be interested to hear what feedback they gave you guys.
So we've been working with them all year, obviously, and the goal wasn't as much to see like to show them and to get like all this feedback on and how we could improve the process. It was more of working with just showing them like how we could implement this system. So we've been working in terms of like how to, and then the feedback loop would be more between us and Dr. Cardenas and the graduate students that we've been working with to implement this system. So the feedback that we've gotten from them has been that we're mostly that I guess what we're doing is to be expected based on the research that they'd done, and then that they seem pretty excited about the work or about how it's shaping up in more of a real world application, if you will.
Okay, thanks.
Yeah, I guess this is Justin again. So interestingly enough, corrosion is kind of my background in industry. Did y'all dig much into the different potential causes of the corrosion and the cracks, or was it more focused on the application of the electroplating?
Whenever we were running our tests, we definitely focused more on electroplating, but we did notice whenever we were kind of taking our breaks with our 10-minute intervals, especially for our benchtop tests, whenever we were taking breaks, we would see some corrosion that was happening after the plating was done. And we figured that would be something that would definitely have to be looked into more if this would be a viable option for AEP.
Okay, so was AEP able to, I guess, explain what their expected corrosion mechanism was? I saw there was some hydrogen pitting in there. Is there anything else going on corrosion wise that they were concerned about?
We didn't really do too much, I guess, investigating in terms of the causes of the corrosion, or you know, like what might cause the cracks or the hydrogen pitting that we dealt with. We did get to go over with them when we went on our site tour about some of the causes of, especially the hydrogen pitting, which comes from impurities in the water that they have inside of their pipes, and it kind of causes that extra damage. But our focus for pretty much the entire year has been, fixing cracks that are already there or that we don't even know are there, rather than like trying to figure out why they happened, or maybe even trying to prevent them. It's been more of kind of almost a reactionary fix, I guess you could say.
Okay, all right, thanks.
Well, at that point, I guess I need to cut in. I want to thank our crack arrest treatment system team for a very nice presentation. We appreciate all your effort and work over the course of this year. It was very well done. Now we want to call up and allow set up for our high efficiency fan filter team. So do we have members of the team on board? Can we hear you all?
Yes, sir.
Yes, sir.
You cannot start your video because the host has stopped it. It
Let me
says,
see if I can fix that.
Same here.
All right, let me see if I can fix that.
thanks.
Anybody else?
Me, sir.
Okay, let me get you fixed up here. How's that?
All right, much better.
All right. All right, you guys go ahead and set up. You got a minute or so here before we have you officially launched, so you can just pull up your slide and check your pointers and everything you want to do. We're not going to start here for another minute and a half or so.
Mason, you on? Yeah, I'm there. Okay.
I think we're ready to go.
Okay, we'll give it a couple minutes here because we want to start right on schedule so that people that are tuning in after dropping out of other session presentations, they'll be able to not miss a beat with you. So go ahead and pull up your, you can go ahead and share your presentation and get it on screen, make it look the way you want it to. All right, I am delighted to present the high efficiency fan filter unit team. They ran one of 3 projects sponsored by Gordon Incorporated out of Bossier. And we're delighted to have you present today, guys. You may proceed.
All right, how y'all doing today? My name is Jose Soto, and I am currently the team leader representative for the high efficiency fan filter unit team. Teammates being Zachary DeYoung as a designer, Shilendra Batari also as a designer, and Mason Wixon as our purchasing representative. All right, let's get into it. Now I'd like to talk about our sponsor, Gordon Incorporated. They are an engineering firm located out in Bossier City, founded in 1964, with our points of contact being Rob Rombo as the manager of engineering and Danny Smiley as an engineer. We really appreciated their help throughout the year. Now I'd like to talk about our faculty advisor as well, Dr. Eric Borquist. Not only does he have 2 bachelor's degrees, 2 master's degrees, and a doctorate, all from Louisiana Tech. He's also a certified professional engineering manager. All these academic achievements combined with his many years of industry experience just made us feel that he was the best candidate to be our advisor for the year, and we really appreciated his guidance and insight.
Okay, so before we get into the problem statement, let's first discuss a fan filter unit and make sure that everybody's familiar with what it is. A fan filter unit is a device commonly utilized in a clean room facility. And a clean room examples are semiconductor manufacturing, pharmaceutical manufacturing, or in general, any environment that requires high standards of air quality. And so a fan filter unit functions utilizing 2 main components. The first of which to be discussed is a motorized fan, which forces air into the clean room at a rate much higher than normal HVAC settings. And this creates a positive pressure gradient between the clean room and its surroundings, which forces air out of the room and eliminates possibility of any foreign particles entering the room from its extremities. And secondly, a fan filter unit utilizes a high efficiency particulate air filter, commonly called a HEPA filter. And this filter basically filters the air supply after it's already gone through pre-filters, and it's just very efficient at catching even the smallest particles and restricts any foreign particle entering the room through the air supply.
Here you can see a cross-sectional image of the fan filter unit currently in operation produced by Gordon. So in the cross-section on the right, there are a couple components highlighted of the unit. Starting at the top, you can see the control panel. This is where air is going to be pulled in by this radial fan. If you notice, the radial fan is set into the blue highlighted block, and that is a subcomponent of the dish pan assembly, which is made of foam. Below that is the sheet metal plate of the dish pan that holds the foam in place and holds everything where it needs to be. So on the left, you can see the isometric view of the dish pan. This is the dish pan in its full assembly. As stated, the radial motor is going to sit down flush to the sheet metal and is going to expel the air radially into this conic cutout, which is going to distribute it evenly within the fan filter unit. Once it's pressed over the top of the dish pan and is forced through the bottom of the unit, it's going to hit the HEPA filter, which is the last means of filtration before it reaches the room.
So if you look at the problem statement, the main goal of this project is to increase the energy efficiency of the overall unit by at least 10%. And to do this process, we replace the current motor that the Gordon is using right now and replace that with more energy efficient motor. And as you can see in the figure, some of the location of control panel, pre-filter, and HEPA filter is listed. So the current motor is located right below the pre-filter, and the intake air passes through the pre-filter, and which eventually passes through the HEPA filter region. So the final design of our project has to match up like certain design constraint. At first, it has to achieve a laminar velocity of 90 foot per minute, which passes through the HEPA filter. Secondly, the overall system has to produce a sound level below 50 decibels. And finally, the overall system has to be as compact as possible.
Now, before we get into the final prototype that we made, I'd like to talk about the other considered designs for this project. As you can see on the left, we have the vertically founded fan mount, which, as Shailendra mentioned, we used the new motor for each of our designs. We took the new motor and attached it vertically as in the fan outlet being directly over the inlet of the unit. But due to the fact that the height was permanent and set at that specific height, we would not be able to do any optimization or design changes to it. And because of that, we did not continue with this design. Secondly, on the right, I'd like to talk about this modified dish pan. And this would essentially replace the original dish pan and allow it to disperse air much better than the original dish pan. But due to the fact that the cost to fabricate a custom piece like this would hastily increase the initial investment for clients or investors, we did not see this as a best suited fit for our design.
Here's a 3D model of the recommended design for the new fan filter unit. So what we did with this unit is we took the fan that pulls air in from two sides and mounted it horizontally above the top of the fan filter unit. In doing so, we allowed approximately 3 inches of clearance between the top of the unit and the bottom of the fan housing. And this allowed for sufficient air intake on the bottom side of the fan. In mounting this fan horizontally, we had to find a way to mount the pre-filters to catch larger particles before entering in the unit, as well as provide some stability for the fan during installation and shipping. So this is where the fan enclosure came into play. You can see the fan enclosure is just a cube that fits over the top of the fan housing and has pre-filters on 4 of the 5 sides. Following the dotted arrows through this image, we'll start with the blue, and this is the air intake from the surroundings. The fan is going to be pulling this air in through the pre-filters and then pushing it to the transitional region. The transitional region is represented by the green arrow, and this will be made of HVAC duct. This is simply going to route the air from the fan into the fan filter unit. Once in the fan filter unit, is going to hit the dish pan and be forced through the HEPA filter. At the bottom of the image, you can see a few yellow arrows. These represent the desired industrial standard of 90 foot per minute velocity coming out of the bottom HEPA filter.
I'd like to talk more about the fan enclosure that Mason was talking about. We essentially needed a way to ensure that the motor would only be taking air that has gone through a pre-filter of some sort, and we also needed a way to attach the HVAC duct to the fan outlet to the inlet of the unit, and the fan enclosure allowed us to do that.
So the figure on the screen is the assembled prototype of our final design. So in our final design, the intake air passes through the pre-filter region. The air is then directed with the help of the transition phase as shown in the figure. And overall air passes through the HEPA filter, which is located right below the overall unit. And the overall air velocity is controlled with the help of the control panel as shown in the figure.
Okay, so initially, whenever we chose this design with the added 90-degree transition piece, we assumed that the losses through this transition would be negligible and not affect our energy savings, but we needed to do an analysis to be sure. In order to carry out this analysis, we designated a control volume around the HVAC duct itself, with the entrance and exits being points 1 and 2. And we then set up an energy balance using the full energy equation in order to do this. But before we could just plug into the energy equation, we needed to first perform some intermediate calculations to find out more about the behavior of our system. And first off, there were some assumptions made in this calculation. We used properties of air at room temperature as a baseline for these calculations, and also assumed steady state and incompressible flow through the fan filter unit. So with these assumptions applied, we then calculated the Reynolds number, and we found that it's fully turbulent flow at 64,500. And this also confirms that it was okay to use room temperature as a baseline. As you can see, the viscosity of this flow would have to decrease by a factor of 30 times for this to transition to laminar flow. So that validated that assumption. And so now that we know that this is characterized as fully turbulent flow, we can now use an empirical equation for the friction factor through corrugated hose tubing, which is the inside of HVAC duct. So once we apply the known values of our system to this equation, we'll find that we have a friction factor of 0.044. And with the preliminary calculations carried out, we can now rearrange the full energy equation to solve specifically for the pressure drop through the system. Whenever we do this, we'll find that we yield a pressure drop of 0.077 pounds per feet squared, or an equivalence of 1/50,000th of a PSI. And this confirms our initial assumption that the pressure drop through the HVAC duct would be minimal and would not affect our power savings.
Now I'd like to talk about a statistical analysis done on the system, specifically a confidence interval. Now, the reason a confidence interval was needed was the fact that air readings underneath the unit, as you can see in the image on the right, will not be uniform. You could have a speed that is different read on one side of the unit that could be completely different than a reading on the opposite side. And this confidence interval just and gave us a way to be certain that readings underneath this unit will fall between this range. And the markings underneath the unit will represented where we measured our values, and having those readings allowed us to calculate things like mean, standard deviation, and confidence interval. And doing so allowed us to calculate the confidence interval of 89.55 to 95.85 feet per minute, which was what we expected.
We're going to do a little bit of bookkeeping here and get into our budget for the project. We were given a project budget of $2,600. We broke that budget down into 4 categories. Our mileage, this is a small amount of our budget. This just was used for gas assistance and multiple trips to Gordon for progress updates throughout the project. Our next section is going to be testing. We use this section to pay for anything that we use to measure and run analyses on the fan filter unit. The next section is going to be prototyping. Here, this is any part, material, fabrication, labor, anything that went into building and producing our prototype for testing was accounted for in this section. The largest portion of this section was $200. We had to buy a large piece of sheet metal and get a welder to fabricate our fan enclosure, and that was the most significant expenditure in the prototyping phase. Finally, we set aside $250 for document production, which just allowed us to reproduce user manuals and final reports to summarize the project at the end of the time. And with all this being said, in summary, we were able to finish the project $735 under budget. So our production budget is what we are estimating it will take Gordon Incorporated to produce this unit and be able to get it to clients. We estimate that cost to be $770, and we did so by using a baseline cost of $550. This $550 is what it's currently costing Gordon to manufacture the unit in current operation. So labor costs and materials are already included in this $550. So to come up with the cost of $770, we used that $550 and just added all material costs and a pre-filter enclosure estimate from Gordon to that $550. So with the completion of mounting brackets, pre-filters, air grills, and the pre-filter enclosure, which is going to be manufactured in-house by Gordon, we came up with the value of $770. So the new unit to the current unit is going to be about $220 more expensive for an initial investment.
So the graph on the screen is a power consumption of 2 motors at a different speed. The orange dotted lines are the power consumption of a new motor, whereas the blue dotted lines are the power consumption of the old motor. And as you can see from the graph, the new motor consumes 4 times less power than the old motor. The standard operating velocity of this overall design is at 90 foot per minute. And at 90 foot per minute, the new motor consumes a power of 28 watts, whereas the old motor consumes a power of 113 watts. And if you do a power consumption calculation between the old motor and new motor, it can be clearly seen that the new motor is 75% more efficient than the old motor, which is directly proportional to the operating cost of the overall system.
Here is a plot of the cost of the new unit versus the cost of the old unit. So these plots and costs were calculated at 5 different velocities at the same 5 velocities as the power calculations. So if you notice, the two graphs are very similar, and that is because the cost is directly proportional to the power consumed by each unit. So at each of the 5 different speeds, there's about $1,000 difference between the lifetime operational costs of the new unit versus the old unit. Looking closer at the industrial standard of 90 foot per minute, there's $1,020 difference between the orange, which is a new recommended unit, and the unit currently in operation. So what we're saying is that right now it's currently costing clients $1,356 to operate one single unit over the lifespan, which is about 100,000 hours, or approximately 11 and a half years. And with the design we're recommending, we think we can get that cost down to about $336 over the lifespan of the unit.
Okay, so as Mason mentioned in the production budget, this new design does cost $220 more upfront. So the question that every client will have is how long until they see their return on investment? And in order to answer this question, we use the same calculation that we did to perform the cost comparison graph, which you can see at the top equation here. The only difference, we rearranged this equation to solve for time, and we set savings equal to the initial difference between the two units of $220. Also note, this equation is based on the continuous operation and the lifespan of 100,000 hours, as well as electricity costs at 12 cents per kilowatt hour, which is the national average at the time of this presentation. So whenever we solve this equation, we'll find that the time for return on investment is 2.46 years. And as a reminder, the 100,000 hours of continuous operation is 11.4 years. So that will leave clients with another 9 years of 75% decrease in their monthly energy costs directed by their fan filter units. So in conclusion, when running these units at 90 feet per minute, you'll find a quick return on investment and a decrease in power consumption by 75%. Are there any questions?
All right, we'll go ahead and use the mode we were in before, where you can, pardon me, you can go ahead and send me a chat and I'll read off your question. Members of the advisory council, please feel welcome to just dive in verbally. Thank you.
Yeah, I'll kick it off with the questioning. This is Justin Bounds with the Industrial Advisory Council. Again, good job with the presentation. Shifting to virtual. So the question I've got is, it looks like you've designed a new filter housing. Is there any difference in the suction surface area for the fan versus the old design? And if so, is there going to have to be any additional investment for the company to get different filters and things like that for the pre-filter?
No, sir. Actually, there is a greater surface area of intake with this new unit, and we ran all tests using the pre-filter that's currently in use.
Okay, so this like the same exact, I guess, dimensions and everything for the current pre-filter?
Yes, sir.
Oh, okay, good. Thanks.
Hey guys, this is Evan Sanders on the advisory council. Also, good job. Enjoyed the presentation. My question is this type thing, is it interchangeable with the things that are already out there? So if somebody wanted to upgrade to this system, does it fit in the same dimensions? It fits right in the same spot. You can just plug and play, do the new thing, and start saving money.
Yes, sir. The bottom of this unit is a nominal 2 foot by 4 foot, which is the same as the previous model. The only difference between this model and the previous is that you have the axial motor mounted horizontally above the unit with the fan enclosure. But as far as grid space in the ceiling, it's the exact same.
Okay, awesome. Thank you.
Hey guys, this is Rachel. I'm with the advisory council too. So with the increased efficiency, do you have any idea on how this is going to change the filter lifespan?
I'm honestly not sure on that one. I want to say that during some of our meetings, we had said that this would increase the duration that you could go between filter changes, but don't quote me on that. Personally, I'm not sure.
All good. I appreciate your honesty.
All right, other questions from Anybody at all?
I've got one more. So this is the fan filter unit for one specific company. Are there other designs out there? And if so, did y'all take a look at those to kind of benchmark any design ideas?
From my understanding, this is everybody currently is using that one fan that's pulling air in from the top of the unit only and expelling it radially. And like I said, this is just my understanding. This company is trying to be the first to use this axial motor to gain the better efficiency. So we did not compare it to other companies.
Okay, thanks.
Hey guys, this is Sam Wade with the Advisory Council. So you guys mentioned a 90 feet per minute. I guess you're aiming for a non-linear or non-laminar flow. Which standard does that come from? Is that a HVAC standard, or do you know?
That was just the clean room standard. Most clean room operations that was provided to us by Gordon. That was the target that they wanted us to achieve, that most clean rooms are operating at. Okay. Is there any opportunity, I guess you're aiming for that 90 feet per minute flow? Was there any opportunity to slow the fan down to aim for a lower flow, and then you reduce your power consumption by operating the fan a little slower? Yes, sir, there was. Right now we're operating at to achieve that 90 foot per minute, we're operating at a flow index of 8%, which the motor's operating at 8% of its full capacity. So we can go all the way down to a 1% flow index, but we were on the lower end achieving that 90 foot per minute, which is why our efficiency was so much better than what it is currently. Okay, thanks for looking at that, guys. That's a good thing to look at.
All right, any other questions from our council or anybody in our audience? We are delighted to have you all with us. We will take a break, and in a couple minutes we'll have our next team load up and get ready to go. We'll start that presentation in about 5-6 minutes. Thank you.
Thanks.
Okay, well, at this point, I'd like to give our next team the opportunity to get their slide loaded up, check out all their audio and video. I'd like to welcome the hitch cargo holder team to go ahead and share your screen, start loading up.
You guys hear me well?
Is that you, Jared?
Yes, sir. It's Jared
All
Sexton
right,
Davis.
very good. I hear you well. I see your screen just fine.
Great.
Who else you got on board today?
We got Justin. There's Mike.
I'm Justin.
Fantastic.
We got Grant coming up soon as well.
Grant's coming up soon.
This is Grant right here.
Hey, Grant. You guys are all coming in loud and clear. So I'm going to clear you to start here in about 4 minutes, all right?
All right.
That way people that want to tune in just in time can do so and not miss a beat.
Thank you.
Well, welcome back, everyone. We'll go ahead and release the floor for our hitch cargo carrier team. I want to thank Grant, Mike, Jared, and Justin for putting it all together for us. Men, it's all yours.
All right. Thank you, Dr. Cardenas. As he mentioned, we are the hitch cargo carrier team. Today, we're going to present to you the results of our final design. My name is Jared Sexton Davis, and with me, I have Grant Camara, Mike Neff, and Justin Sutton. And our sponsor is David Grimion, and our advisor was Louis Reese. So just a little preview of what we're going to be talking about today. First, we'll give you an overview of our project and introduce our sponsor, some of the design requirements that our sponsor required. We're going to break down the design that we finally went with, mention some of the quantifiable values to show off our success or not, and then the performance and design analyses of an engineering analysis, and then show our next steps of design. And so, of course, as you're all aware, we've had a couple of changes lately due to the state of the world at the moment. Since we have no in-person meetings, we've transferred to Zoom meetings, just like we're doing right now. And we didn't get to, by the end of the winter quarter, we weren't able to implement or be finished with the project like we were planning. And so since it's a very physically large project and we didn't want to ship it anywhere because that would be very costly, we delegated certain tasks to each individual, and then we'd meet up as possible to implement all those together. And then, of course, some performance analyses would be impossible with current states of affairs, and so we're going to replace those with more engineering analyses. So a little bit about our sponsor. His name is Mr. David Grimion. He has a family of 10. He's a Louisiana Tech alumnus, and he has an independent venture called Excellence and Innovation in Motion in Monroe. So just a little bit of what our project was, the basics of it. Our sponsor desires additional vehicle storage, which can be accomplished by a couple of different options. Two below on your screen are ones that are already available on the market. The one on the left we refer to as an eggshell, and we'll compare it to this product throughout the demonstration a couple times. And the one on the right just attaches through the hitch of your vehicle. And so our sponsor wanted one that attached through the hitch as well. He wants it to slide or rotate away from the vehicle for trunk access. And he wants it to improve upon the two existing solutions you see here. And so just a couple of requirements that our sponsor requested. It needs to hold at least 150 pounds, or at least 150 pounds of cargo capacity, whether this be groceries, sports equipment, luggage, anything. It wants trunk access, as previously mentioned. It wants minimal fuel economy reduction, and we're basing this off of a comparison to the other two options on the market that we just showed you. It needs it to be water resistant, so it doesn't get so the insides don't get wet in weather conditions, and of course it needs to meet Department of Transportation regulations. So next, I'm going to pass it off to Grant to talk about some of the basics of our design.
Hey, this is Grant here. We are about to dissect some of the construction of the enclosure. So this is just a simple breakdown of the different layers that we have. We have the white paneling, which you can see are high density polyethylene sheets, HDPE, which are about 3/16 thick. And then we also have the aluminum extrusion frame. In your top right corner, you can actually see a cross section of it. It measures 20 millimeter by 20 mil. And it is 80/20 aluminum. And as you can see, it has slots on each of the sides where you can put the T-nuts through and actually mount the polyethylene sheets to them. Next slide, please. So here we have an open view mounted on this truck, and we took off the doors so you can see the actual frame itself. So we actually have the aluminum extrusion frame in the corners with a little more complex design than you saw in the last one. And if you look down below, we actually have the steel tube hitch insert, which is also 3/16 thick and A500 steel. And you can see a little bit of the slide railing, but we'll get into that more later. And also as a note, the trailer lights that we have on here are mounted on temporary posts, which due to the COVID-19 situation, we were not able to fabricate as shipping costs were expensive. So we met up with our sponsor, David, and decided that we would mount some temporary posts for now and give some further detailed plans for welding permanent guide posts onto the sides here. So that's what that C-clamp is holding up right now. Next slide, please. So here we have a little bit of a side view going, and you can see the trailer lights where they attached. We also have our railing again going down the side, and then a new spot for your license plate holder, which could impair the vision if it were on your vehicle. So we gave a new spot for that. the 10-inch pneumatic wheels, so you can dismount your enclosure from the trailer hitch and roll it away. And we did some ergonomic handles, which help improve the dismounting and mounting process. Also, you can see in here that we have 150 pounds of weight inside. We did 50-pound bags of some feed just to see where we were at. Everything worked nicely and great. Next, we're gonna show you a little bit more of the actuation and how to dismount and mount this. So can we go to the next slide, please? Here you can see it partially mounted. We have some roller rods, which you can get better images of further down in the slides. And we slide this enclosure all the way off, and then we rotate it away from the vehicle so that the door of the SUV can actually open, the hatch fully open. And then from here, you can actually slide it away. So the next two videos we have are just for the actuation from different angles, so you can see more of what we're talking about as far as the mounting and dismounting process goes. So you would pick it up, pull it off, slide it off. Here it would touch down at the ground at the angle, and then you would be able to unhitch it from there and roll it away, given the two notches in the railing system, which you will also get a better view of later down in the slides. So can we go to that side view? Next slide, which is basically the same thing, but now what you can see here is the notches themselves as it clinks down, and then you can disarm it from there and roll it away. All right, next I think I'm going to hand it over to Justin.
Okay, so here we have some pictures of those positions he was talking about earlier. So on the left, we have the resting position where our roller pins are resting in that back notch, which you can see all the way to the right. And in the middle picture, you can see that the roller pin has now been detached from the hitch insert, and now the structure can be rolled away from the vehicle. Next slide, please. Here we have our fully mounted position. This is the position in which you will be driving your car around with the structure fully loaded. And on the right, we have a picture of the roller pin, and it is currently resting in the notch closest to the vehicle. Next slide, please. So for our rolling pins, we use Delrin rods. Delrin is the product name of an acetyl polymer that has very high strength, and it is used to replace metal in a lot of applications. So it has a lot of the properties that we were looking for in a roller pin. Next slide, please. So here we have another picture of our hitch insert. And just to clarify the location of our notches, we have two towards the back of the vehicle and two towards the end of the hitch insert. Next slide, please. All right, and here we have another picture just to show you our resting notches. As you can see, we have the back resting notch and the front resting notch, as well as the entry for the roller pin. All right, next slide, please. And here I'll pass it back off to Grant.
Grant here. So this is actually a previous design that we had earlier in the stages, where you can see some of the handles. They're a little more shallow. We were playing around with different ideas, more ergonomic handles. As you can see, it was difficult to put on this vehicle, which is a little bit smaller than the vehicle that we intended it for, which is the Ford Expedition. Later on, we actually changed the handles, as you saw earlier, and we're going to look at some graphs that actually show the mounting and dismounting times in a bit. but we can go to the next slide and see a little more of the construction. So here's a really good picture of the different layers that we have. You can actually see the 80-20 aluminum extrusion. And then you actually have these weather stripping, which we had to add later. It provides a better fit, more snug fit for the panels. And also we're getting less water in the actual enclosure itself. And also you can see here in the left picture. And this is how it would mount to the paneling. So you would have a screw go through the HDPE, which would go all the way to this nut right here, and then it would fasten and lock against the aluminum extrusion. So we can go to the next slide now. Again, here's just another video that you saw from earlier, and this is the actuation that we will be talking about. And just to remind you of what we're working with and what we're dealing with. We can go to the next slide, which goes over our quantifiable values. So we will be going over the factors of safety, which include the wheels, the hitch insert, the roller brackets, and they go over a few different loading scenarios for when you're mounting it, as well as when you're driving with it, which would be our fatigue loading. And then also we're going to go over a little bit of the fuel economy reduction, which was a big part of this. And that was an alternative to the eggshell cargo carriers, which can be on the top of your vehicle and potentially reduce the mileage by 20%. We've even actually read articles as much as 30%. So here are some of the trials that we have, and after this slide, we're going to follow with a graph so you can see it more clearly. While we were mounting and dismounting the enclosure onto the hitch, you can see that the mounting process takes a little bit longer than the dismount, and this is due to the fact it's harder to see the roller pins get into the slides. So we actually accommodated this with the ergonomic handles that we added. So you saw a picture of the ones we had on it and then the ones that we added on it, making a total of 4 handles now, which actually helped quite a bit. And also we noticed that aligning it was very important. So we knew that we needed to add the guideposts to help us better align it and also better secure the enclosure to the actual hitch, which we will see later. But we'll go to the next slide now, where you can actually see the graphical representation of what I'm talking about. So your average mounting time is 17.8 seconds, and your average dismounting time is 3.5 seconds. And we did a total of 5 trials. And actually up next, we have Mike, who will go over some of the factors of safety.
Hey guys, Mike here. I'm going to talk about some of the simulations and such that we did to make sure that our structure was as strong as we were hoping it was going to be. So this is the loading scenario that we run into in that fully mounted position. We have the roller bearing is in the back notch, and we have the front of the enclosure resting on the front. So we ran this through a SolidWorks static analysis. And we found that our lowest factor of safety anywhere on the structure was 3.8, and that is in that back notch. Next slide. So when you're driving down the road, the enclosure will be in that fully mounted position. So we also did a fatigue analysis to make sure that over multiple applications of the force that the rail would still not fail. What you're seeing here is we did yet another SolidWorks simulation. And this is showing that it's rated for 1 million cycles. And according to most of our statics textbooks and things like that, once you're rated for 1 million cycles, they call that infinite life, which means we just don't have that the loading scenario is not enough that we have to worry about any failure due to fatigue. Next slide, please. So this is the partially mounted static analysis, and this is what we were showing as the loading/unloading position, where the enclosure is supported both by the ground and the very end of the rail. And we found a factor of safety of 3 for this. Next slide. This is the roller bracket that's sliding up and down the rail. We did another SolidWorks analysis and found a factor of safety of over 12 for this, which was a little surprising. We didn't expect it to be quite that high, but we're happy it is. Next slide. And this is that same loading scenario, but in fatigue, because again, the roller bracket will be undergoing a fluctuating force due to bumps in the road. And we're rated at over 1 million cycles or infinite life. Next slide. We did, so because of COVID-19 and things like that, we weren't able to do an exact fuel efficiency test with our product on the car that we designed it for. So we settled for a SolidWorks fluid flow simulation. This is with a wind speed of 30 miles an hour to simulate driving at 30 miles an hour. And you can see by the flow trajectory lines that our enclosure is fully within the wake of the car. This is also reinforced by the graph below, showing that there is no downward force, that there's actually a slight vacuum where the enclosure is because it's within the wake. Next slide. This is the same thing, except now it's 60 miles an hour. And again, you can see that we're fully within the wake of the vehicle, meaning that there's no drag force and it shouldn't really affect fuel efficiency in any way. The next slide is for comparison. This is that eggshell design. So I ran the same simulation with that, and you can see how not streamlined the flow trajectories are, and how much it messes up the wake of the car and how much interference there is. And that's reinforced by the graph below, showing that the eggshell itself has to withstand at points 67 pounds of force, of just normal force to its surface, because of where it is on the car when the car is moving that fast. Next slide, please. I'm going to pass it off to Jared to wrap it up.
Hello guys, Jared again. So before we wrap it up, just want to talk about our budget just a little bit. We were allotted $1,375 so far, or we only spent about 100 below that, so $1,274.50. So we're still 100 under budget. Just a kind of a breakdown of what parts of our budget cost the most. The materials you see was by far the biggest category, coming in at 68%. This included the HDPE, which was the white paneling on the outside, and the raw material for the hitch insert. Then the hardware mostly included screws or various nuts to secure the structure. And then lastly, we have a category for special, which is costs that were accrued due to state of the world with COVID-19 right now. As you saw, the C-clamps, for example, were a intermediate kind of step. They weren't ever supposed to be permanent, and that's not what we designed the project to look like. But we presented David with a couple different options, and he told us just a proof of concept would be fine for right now. And so that's what that cost category was. And then these were some of the additional modifications that we've most recently made here in the spring quarter. There's spacers for the structure. If you notice in one of those pictures, whenever it's in the resting position, the front of the structure has a little bit of a downward angle to it, and those spacers would help it to sit up straight. The alignment post in red in this picture was something that we were planning to add this quarter, but weren't able to. And if you notice, we have that frame, and that's what our temporary solution for that is. And then the expanded metal platform on the bottom of it to give whatever items you place into the structure, into the enclosure, a little bit better spot to lay on. And for this quarter, we just put wood on there, which that served us very well. And then finally, I just want to go a little summary of our design requirements. The load capacity, this picture is an example of what we did for that, and it easily held 150 pounds, and I don't believe we had any concern of it being in any rickety shape at the moment at that time. And then the trunk access, that was covered by the actuation, as we showed multiple times, it actuating away from the vehicle, and you would be able to open the back door very easily. The fuel economy, as Mike said, we weren't able to generate a hard number for that due to testing situation, but we were we're able to confidently say it's more fuel efficient than the eggshell design, because the only difference would be the increased weight, but we believe that would be minimal compared to the drag, or the less drag compared from the eggshell to our design. The waterproofness, the test that we did, concluded that we had about 80% waterproofness just from the different trials that we did. And then it does meet Department of Transportation regulations. And so that wraps us up. Does anyone have any questions for us?
Hey, this is Matt Wallace with the Advisory Council. I did have a question. I noticed in your analysis for the safety factor of the structural capacity of the frame, it looked like it was loaded uniformly on either side. And I was wondering if you had thought about doing some torsional analyses, actually loading just one side of the frame and introducing a torsion to the connector tube to the hitch.
I'll take this one. So we didn't do. So you mean to load just one side of the U-shaped rail?
Yeah, let's say like in your picture that you have up there, let's say both those bags, he took a corner and they all, swung to one side instead of loading it uniformly. And so he goes over a bump and those things pop up and, come down on one side of the frame instead of uniformly loading it.
Okay. We didn't specifically test that. What I did do and didn't show on here was that the analyses that I showed on here were for it was a 250-pound load, which actually includes the weight of the enclosure plus more than the 150-pound capacity than we were looking for. But previously, I have done a calculation with over even 500 pounds of that same load, which doesn't exactly compensate for that torsional factor, but it gives me confidence that it would be okay. But that is a good. Thank you for that suggestion. We'll include. We may include something like that in our report.
No, yeah, did a good job.
Thank you.
Hey guys, this is Evan Sanders. I was pretty impressed with the flow simulation, doing fuel economy testing and stuff like that. I thought that was really cool to see. One question I had was, did you compare to like a baseline? So you compared the difference between, or you showed the comparison between using this one or using the top mounted cargo holder, but what about just like a car by itself? Did you compare to that to kind of see if there was any change at all there?
The main thing we were testing with the flow simulations was specifically the force of the wind on whatever enclosure we were looking at. So no, we didn't test specifically because within that simulation software, there's not really a way to test for fuel efficiency by itself. So because we couldn't do efficiency by itself, we kind of backtracked a little bit and we're just trying to test drag force.
Okay, cool. Thank you.
Hey guys, this is Sam with the Advisory Council. Yes, I'd back up Evan there. Using the SolidWorks to do those flow simulations is a very powerful tool. So I'm glad you guys were able to utilize that for your project. Those graphics are a very good visual for positive reinforcement for your project. If you are using this as a marketing type presentation. You guys mentioned it meets DOT regulations. So what exactly does DOT say about these type of enclosures or extensions of your vehicle?
So I think I can take that question. Actually,
We're gonna have to do it kind of quickly. We'll have to wrap up here in a couple minutes. All right, man?
Yes, sir. Sounds good. So on that point, we actually, it was very hard to find information on this type of thing because of course it doesn't have its own axis, or its own axle, excuse me. And so we actually did a DOT light kit. Therefore, anything hanging off the back of your car is marked off. Not only that, but it has blinkers in running. Also, we and we kind of treated it like a trailer that you would have for a boat. So not only that, but another thing that we did not mention that we added was it has eye bolts in the back of it that are on the enclosure itself, and then those are safety chained to the back of the vehicle. So that would be another safety. And ideally, we also wanted pins to be on the guidepost that would also fasten the enclosure to the guidepost to be more. But thank you for the question.
Yeah, thank you guys. Great job. Good luck to you guys.
All right, well, we got time for another quick question, but it'd have to go really fast.
Yeah, I've got a question. Justin Bounds here with the Advisory Council. I guess could y'all explain a little bit the assumptions you used in your fatigue loading calculations?
Of course. So I assume, so in the simulation we set it up to assume for what we were trying to simulate was just really big bumps in the road. So we assumed like a max force of a little bit more than what we anticipate or the enclosure itself is around 65 pounds. And so plus the 150, we did a little bit more than that at like 250 pounds. And so we had an alternating force between 0 simulating free fall and then the 250 pounds.
Okay, thank you.
All right, since I was just looking at the schedule, we do have a break coming up, and I did have a couple of questions come up on chat. I'll read off the first one, okay? The first one is, if we have time, can you explain assumptions in fatigue loading?
Yeah, that was my question. Sorry about that.
Okay, well, I'll move on to the next one. If this went to market, what would be expected? What would be the expected selling price? How does that compare to other cargo expander options?
So I will take that question. We actually have a price breakdown in our spreadsheet for how much we purchased everything for, obviously, and we're around $1,200. This is something that actually we would need to talk to David with because there's multiple different routes that we can go. Originally, we were thinking that the enclosure could be injection molded, kind of like an ice chest. But here you can see that we went with the panels. And Dr. Cardenas actually brought this up, but when we use the panels, you can actually possibly sell this as something that the buyer could, or the consumer could actually assemble themselves because everything could be flat and shipped in a box that's much smaller than this. So we don't actually have any prices for selling at this moment, but that would all depend on those two details, which we would have to get with our sponsor, David, on. Thank you.
But part of that is we would expect it to be a little bit more expensive just because it's providing more than, say, the flat surface that we showed at the beginning that just goes into your hitch. This is providing more waterproofing and significantly more enclosed space. So it would be a little bit more expensive, but there's not a direct, there's not any really good direct comparisons on the market right now.
All right, any other questions on this one? Well, our advisory council is due for a well-deserved break. We thank you for your intense attention and good questions, and we'll reconvene here right at 3:30.
They're doing.
And so at that point, we'll jump back in with our diversion control system. Thank you all. See you back here at 3:30.
It's the team.
Seasons of magical adventures, they took on new roles and challenges. Welcome to Watch Mojo, and today we're counting down our picks for the top 10 Wizards of Waverly Place cast members. Where are they now? I love you too! Number 10, Bridget Mendler. After the end of the show, she continued working with Disney as the star of Good Luck Charlie. Oh my god, we don't have noses! When that show finished, she found further TV success on series like Undateable,
Hey,
Nashville,
Madison, can you mute yourself?
Happy Whatever. He also produced new music in between.
Sorry.
Welcome back. And at this time, what we'll do is we'll allow our diversion tote control team to go ahead and start their screen share and get set up and get ready to present here. And we'll check your audio, we'll check your video, and get you ready to roll. There's Matthew. How are you?
Doing well.
We're just waiting on our other two teammates to finalize their stuff, and then they'll jump on real quick.
Okay. Well, you can start playing with your file, unless they're the ones that have it. That's fine too.
Reese, you want to turn your
So Matthew, are you the one sharing your
I
file
am.
and advancing the images, or is that a?
No, I have it. It's just
Oh, you have it? Okay.
I'm just waiting.
Feel free to put it on there and see how it looks.
How's that looking?
That's looking great. And do you have everybody on board here?
You all ready?
All right, well, we'll give it another 30 seconds here since people are dropping in at precise times in order to not miss different presentations, including yours. So we don't want to cheat them out of getting all the lowdown from you. All right, I trust everybody had a restful break, and now we're ready to bring on board our diversion tote control system team. I want to thank both the Matthews and Ryan and Jason for putting this together and the large effort throughout the year. Men, you can take it away.
All righty, thank you. Well, as Dr. Cardenas just said, that we are the Lamb Weston Diversion Control Tote Control System team. My name is Jason Wallette. I was the purchasing manager for this quarter. Matthew Mueller was our team lead for this quarter, and our two designers were Matthew Mitchell and Ryan Rothenberger here. First, we're going to take you through the background and let you know a little bit about Lamb Weston and our help from them. And then we're going to take you through our problem statement and then give you an idea of the sensors and indicators that we used for this project, and then our cage design. Then we'll run you through both our budget and the procedure that we went through in this full design. And then lastly, we will take you through some of our engineering analyses and the performance evaluations we did. And then at the end, we hope to give you a little demonstration and take any questions that you might have. All right, so this is Lamb Weston. They are in Delhi, Louisiana. This is their sweet potato processing plant, as you can see in the photo in the top right corner. They opened in 2010, and this is their largest sweet potato factory. Our sponsor contact was Derek Newman, as you can see in the lower picture here. He helped us throughout the entire year on any questions that we had. So our big problem statement was to reduce spillage in the overflow area. In the overflow area of their factory, we had fries that were falling on the floor, and so far the FDA has not considered a 5-second rule yet. So any fries that hit the floor, they were waste, and we needed to reduce the waste for this company. As you can see in the upper right picture, this is the overflow area. Fries would come down to this area when the baggers couldn't keep up, and they would go to this shaker that you see here at the top that we have labeled, and this shaker would let the fries bounce along into these totes below. Well, in between the totes and the shaker are these pneumatic gates that would allow fries to either fall into a tote or move on to the next tote. Now, there's nobody to monitor this area constantly. So the problem was these totes would get would fill over and fries would fall on the floor. Sometimes the totes wouldn't get in the same places, fries would fall on the floor. So there was that problem. Now, the problems we had for our design was that this conveyor is constantly shaking when fries are coming to this area, so there was nowhere we could attach to it. These totes, we were not able to alter them because they come pre-made in just the square cardboard boxes on pallets. And as you can see in the lower photo, there's a limited amount of space that we have down here to work with. So we needed to figure out something that would be able to work in that area. Now, I'm going to let my teammate Ryan move on to the next slide for you.
This is our design matrix. One of the things that we highlighted as something important that we needed to tackle was the totes not being in the exact same spot every time. So the 3 ideas that we came up with was a full cage, a frame that attached to the legs of the shaker unit, and just an L bracket on the floor. That way the cage would be in the exact same spot every time, directly under the pneumatic gates. Our design matrix can be seen above. Our categories were effectiveness, cost, food safety, personal safety, and durability. Our top ones were effectiveness and cost, because if it's not effective, then what's the point? And if it's too expensive, then it also is not a good idea. Food safety was also very important because it's in contact with fries at all times, most of the time. As you can see, the cage was the design that we finally landed with as being the best coming out of this design matrix.
So I'll be going over our indicators that we've used in our project. So our first indicator is our light sensor. And so as you can see, it has a green and red light. Now, once the green light is on, that means there's no need to check the tote. Everything is good and you can just walk on by. The next is our red light. If only the red light is on, that means our distance sensor has tripped. And this means that a worker will need to come over with a rake and rake down the fries. Because what happens as these fries fall into these totes from the shaker, it forms a hill. And so to untrip the distance sensor, all you need to do is just rake these fries. And then next is our indicator for a weight sensor. Now, our weight sensor is indicated by when both the green and the red light has tripped. And this means that a forklift driver needs to come over and remove this tote. So next is our weight sensors. And so we use an FX19 compression load cell. And we used 4 of these on our cage design to get up to our max recommended weight of 800 pounds. Now these totes will typically be filled anywhere from 700 to 800 pounds, which is why we went with these. And it's not stated on the slide, but these weight sensors can go up to 250 pounds of weight, but this can cause some damage to them, but we don't expect to ever go this high. So this is why we went with these cells. Next is our distance sensor. Now, one thing that we liked about this distance sensor is that it was nearly plug and play. You can always just adjust your distance from the sensor itself. There's no need to program it, which is one thing that we liked. Now, since this will also be in a cold environment, this shaker assembly, so we got us a distance sensor that is rated from -25 to 60 degrees, which makes it pretty good.
This is Matthew.
And also, since it is dust and liquid tight, we don't have to worry about any food debris or any moisture buildup damaging it.
Miles went early. I missed his. He's the only one I really wanted to see.
All right, next we're going to go over the final design of
final design of our project, we did one solid cage that's welded together with carbon steel to be bolted to the floor.
At least they said that.
A piece of sheet metal would go over the tabs on the four corners that you can see on the bottom here.
This is Matthew.
And where?
Yeah, I know.
There we go. All right, so we'll have the distance sensor. You can see in orange
Hang
up
on
at
a
the
second.
top. We have that.
Hang on a second. I'm hearing some background noise from other conversations. If we could quiet the meeting room and allow our speakers to continue. Thank you very much.
Thank you. So yes, our distance sensor is in orange up at the top. We have that offset towards the back in order to prevent damage from when the tote is loaded. Our weight sensors will be on the tabs on the bottom, so it's not directly on the concrete floor. With the sheet metal, we'll cover all of them on top of that. And lastly, we used an Arduino for our prototype, which is found in the box at the back of the cage to wire this all together and make it all work. Next up, we can see what the tote will theoretically look like inside of the cage. You can see the green lining on the inside, which is what they use for food safe plastic to make it safe. Now, next up, we have our budget. Here we have a simplified budget for ease of use. We start out with $1,145, and we unfortunately went a little bit over that, but it wasn't too much of a concern. On the left, you can see the suppliers for everything we needed to get. At Lowe's, we got things such as bolts, nuts, washers, wiring, piping to keep the wiring safe. Thankfully, next up, we have Hawkeye Sheet Metal, who gave us our sheet metal at cost. Shout out to them. Alpha Welding is who we had fabricate the cage itself. Granger, we got our distance sensor from, and we have a few other things like electronics and paint from other sources.
This is our procedure that we went through. Once we got the cage from Alpha Welding, we finalized our design for the cage and then got Alpha Welding to produce it for us. And once we received the cage, the first things that we started doing were drilling holes to mount our conduits for the wires and placement of all of our weight sensors. We had to cut and clamp the piping for it to the cage itself, and then attach the sensors to the cage and the Arduino to the cage. And we wired in the light and all of our sensors to the Arduino. Once this was done, we calibrated the weight sensor and the distance sensor with the code that we had set up. We collected data from that and then continued to run simulations to make sure that the weight sensors and the distance sensors did what we were planning on them to do. This is a snippet from our overall code flow chart. This runs constantly and checks all four totes multiple times to make sure that the weight sensors haven't tripped on any of the totes, that the distance sensor has not tripped on any of the totes, that a tote is even in the hole, because this code controls the doors itself too. But it also allows for manual override for the doors. That way, if someone comes over and breaks the fries down and there's more room to add, they can open the door and then the code will leave it open until it trips again. This just shows that it checks for each door, it'll check the tote and the other totes to see the state of each of the totes. That way it doesn't just shut a door and then open a door over something that's already full or not even there. This here starts our engineering analysis portion of our presentation. This first one that you're looking at now shows a pallet and what happens when it collides with the cage, because we figured that the first form of failure that we run into would be someone driving a forklift and missing the hole in the cage and just ramming it into the cage itself. We put this into SolidWorks, had a modeled pallet made out of pine wood and our cage little section as seen there. And in putting 600 pounds of force, 650 pounds of force on this, neither one broke, but it was enough to deform the cage. So this analysis just shows that a pallet could withstand a force and that the cage will bend if they do run into it.
So next up is our bolt analysis. And that's to mount the cage to a concrete floor. We will be using grade 8 half-inch bolts, which will be 2.75 inches long. Now, after doing some calculations, I found out that the first mode of failure that will occur is in the cage itself at the mounting hole due to bearing stress. Now, what bearing stress is in this case is that the mounting hole will oblong itself. And so the cage will still be attached to the floor from the bolt, but it will have a little bit of a wobble in it because now the mounting hole has been oblonged. And this occurs at a load of 2.27 kips. And then another interesting thing that I'd like to mention is that the next form of failure that will occur is edge shearing at the mounting hole. Now, what edge shearing is that instead of the hole oblonging, the mounting surface itself will actually shear from the hole itself as like a crack, and a small chunk of the cage will break off, meaning that now the cage will no longer be attached. And this occurs at 2.62 kips of load. And so basically what will happen is that the cage will break first before the bolts do. And so next is an engineering economic analysis for a 5-year cost. Now, I based this off, to get our interest rate was based off an average inflation rate. And the cost of the cage setups is that there are 4 stalls, so you'll need 4 cages. And this is all assuming our current sensors that we have and not including our recommended sensors. But as you can see, in total of including the cost of all fabrication, sensors, and electricity costs, the cost of only 4 cages will cost about under $5,000 once you add up 5 years of costs. And then next is if we were to hire 3 workers to do the same job as our cage design. And this is based off minimum wage and assuming no overtime for these workers. And what I've found out was that after 5 years worth, if you bring all that cost into a present day value, it'll cost under $294,000. So as you can see, this cage design is pretty worthwhile for just money costs.
Okay. In order to calibrate our distance sensor, we devised a simple test in which we took a ruler and attached it parallel to the line of the laser from the distance sensor. And we ran an object closer to the distance sensor until the distance sensor tripped. Now we did this at 3 different distances and 20 times each time, so our sample size is 20, in order to figure out which distances would be the most accurate for a recommendation at where to place the distance sensor and what angle we want the distance sensor at in order to read. Once we had the data, we made a 95% confidence interval using a t-distribution due to the sample size, and we found that our 20-inch distance had the smallest confidence interval and the least absolute error. So that is the distance we went with for our reading on the distance sensor. We also performed a similar calibration test for our weight sensors in order to find the calibration factor in the code. Now, when we were at Lamb Weston testing our cage, when the forklift driver put a tote into the cage, he was very careful, he was very safe, took his time. We were very thankful for that. We didn't want any damages or anything. But it did take a while, and we were concerned that if there were delays in putting the totes into the cage every time, that this could cause a backup and cause more problems than we were solving. So we devised a simple test Matthew did here to drive a forklift into 2 different areas to drop down a tote and see how long it took. We did one with the cage size, so approximately 3'10" by 4'2", and one larger area to see how long it would take. We found from this that with the cage, it takes approximately 1 to 2 more seconds with the cage present to load the tote. but that's not a significant enough time to worry about delaying the line, thankfully. Last stuff, why should you care about this if you're not Lamb Weston and you don't like sweet potato fries? Well, for health concerns, with the cage present, we have less worried about things coming in contact with the tote to puncture it, say for instance, and contaminating the fries. We wouldn't want anything like that, and the cage helps prevent that. For safety reasons, we have the light indicator up at the top, and this prevents people from walking across the line where the forklifts drive to check on the totes. And the less times you have to cross that line of traffic, the safer you are. And obviously for economic, the less fries wasted, the more money Lamb Weston can make. Also, the less fries wasted, the less sweet potatoes are required from our farms. This would be for environmental. Next up, I'd like everyone to go ahead and click on Jason and in Zoom. There's little ellipses there. You can pin the video. And I want you to do that so you can get a bigger image of Jason and Ryan here as they show our project in action.
Okay, thank you, Matthew. We just wanted to give a quick demonstration. As you can see, this is our cage unit here. This is where the totes are going to come in at. And what we wanted to show real quick was just this light changing for the different variables that we said. As Ryan shows right here, whenever you get in front of the distance sensor, the light has changed to red, indicating that the distance sensor has gone off. And then whenever whenever there's nothing in front of the distance sensor, the light has changed back to green. Everything is good to go. And then as you see, if I put weight, we have recalibrated it to read for my weight. As you see, both lights have come on to red and green, indicating that the weight sensor has tripped and it's time to come get a tote. Whereas when I step off of it, the light resets back to green and everything is ready to go. So we just want to give that quick demonstration.
All right, do we have any questions?
All right, if you're just joining us, we'll go ahead and encourage the advisory council to go ahead and ask questions verbally. And since we have a lot of people attending, if you wouldn't mind sending chat messages, that would also be helpful.
Hey guys, great project. This is Evan Sanders here on the advisory council. I had a quick question. I like your setup there with the rails. Was there any comparison done? You have like a welded assembly there. Were there any type of different type of materials, railings, different type of things used or considered for the cage, or is this something you just guys picked and went with, or how'd you decide upon that?
Well, in the initial consideration, we decided to go with the rails because with rails, the workers were still able to reach in and get a hold of the tote, or if work was needing to happen within the cage itself, whether the sheet metal needed to be removed, workers were able to reach in and grab where is needed. Whereas with walls, it was kind of all you could get in from was the entrance. And we wanted to make this cage as open as possible for the workers to get wherever that they needed.
Great, excellent, thank you.
Hey guys, this is Sam with the advisory council. Thanks for doing the demonstration. I'm glad you guys were able to do that, show off your work. So thanks for doing that. You said that part of this was to reduce the waste of fries falling on the floor. Were you able to quantify that on what your savings was, or was Lamb Weston kind of keeping that, to themselves?
Unfortunately, Lamb Weston did not have any numbers available for current losses on fries. They just knew that it was a problem. So realistically, a test in order to see how much was wasted would be very time consuming and cause a lot of unnecessary downtime for the plant. So we were unable to come up with an exact quantified number for that.
Okay, that's fine. Yeah, I mean, that'd be kind of a long process. You'd obviously put this in service and run it for some period of time or something. But anyway, thanks, guys.
We also had to deal with the COVID problem where we couldn't actually go to the go to the plant anymore at all this quarter. And we only had one cage and they've got 4 slots. So I guess you could figure it's very difficult to figure out how effective one cage would be when in actuality they would have 4 for all 4 tote slots.
Yeah, that's also a good point that you guys added such emphasis on the safety factor for these things, because forklifts are very dangerous within these plants. So thanks for looking at that as from a safety perspective too.
Hey guys, Justin Bounds with the advisory board as well. Good job with the project. Very good looking final design. I'm curious to see. You mentioned on the anchor bolts anchoring the cage down into the floor. One of the main failure mechanisms was going to be in the rail. Did you consider, I guess, failure of the concrete floor if it would crack or chip? If you run into it with a forklift or just over time?
Well, I tried looking into more on like about concrete, but it's like I wasn't too confident on like what I found, so I mainly just stuck with the bolt analysis and then like analysis of the cage. But just due to like just some constraints of like not having that great of knowledge on concrete, I wasn't able to do a sufficient look into that. But I mean, that is a good consideration to take.
Okay, yeah, I appreciate the answer. So I'll give. Well, I guess I've got another question. Is Lamb Weston going to implement this solution?
Well, they're picking it up and taking it back to their plant, so we hope so. If they will implement the project, they will. They plan on an expansion to their plant sometime in the near future, so they'll probably run some tests with it, see how effective it really is, and then when they do that expansion right next to where the overflow area is, they would go all in for all 4.
I can tell you that one of their representatives is attending the meeting, and they asked for an opportunity to comment after the questions are done. So we'll get to revisit that question.
Oh, great. Yeah. Thanks for the input. And, I guess from my experience in industry, I would recommend you look at, drilling holes into the concrete and setting like some anchor bolts and like an epoxy. That's typically how these types of things are attached, or just steel structures are attached to concrete. But overall, good project. Good job, guys.
Thank you.
Yeah, but there are 4 mounting holes currently present on the cage, so it is ready to be mounted to the floor.
All right. Any other questions from our audience or our council? Well, at this point, I'd like to yield the floor for a moment. Derek Newman, a representative and mentor and sponsor for this project from Lamb Weston, is joining us. And Derek, welcome aboard. And I would love to hear from you.
Hey, Dr. Cardenas, we've got a couple of us here in the room, and I think some of them had some comments to make. So I think Thomas.
Yeah, I'm Thomas Proger, the plant manager here. And I want to thank Henry. Thank you very much. Thank you to the university. This is a great program we are proud to participate in. I want to thank the design team and maybe answer some of the questions here. As a matter of fact, if we were to add one dimension to this, and it would be a vibratory shake, we are actually considering looking at this design to add to our current tote dump over what we call the overflow area. And that could really, I think, complete this design to where we feel that there's a really good application for us here in the plant. Meaning a side-to-side movement, as the students explained, that mounding of the French fries as they come into the tote. So we would work on it, but certainly the team likes the load cell, the weigh cell, and the combination of the visual indicator that we would then add to our program for the tote, the automated. I've got Randall in here, I think wants to say a few comments as well.
Yeah, this is Randall Veazey. I'm the engineering manager out here. But yeah, great concept, and I think you know, the team definitely accomplished what the goals were as we set for them at the beginning of the project. And yeah, you know, is it something that we'll look to implement? I certainly think so. You know, to get, of course, that's as y'all mentioned, it's a heavy forklift traffic area. Forklifts are very dangerous, so the more people we can get out of that area, the better. You know, the perfect scenario would be, you know, it's a completely automated bulk off system to where, you know, a forklift comes in, gets a full tote and puts an empty one in there. So I think the concept that they come up with the load cells, with the you know, level sensors, you know, would allow us to integrate into our existing bulk off system to where, you know, we could tell the dropout gates when to open and when to close and when to move to another one. So, you know, like I said, the concept is there, and it gave us, you know, a lot of things to think about. You know, like Thomas mentioned, you know, we have a lot of mounding in those totes, and put some sort of vibratory shaker that will settle those fries out in the tote and make them level, you know, would be a part of what we would implement here, along with the concept that the guys came up with. So, yeah, I mean, I think it was overall a very successful project from our side. So we appreciate the guys' work, and they were a joy to work with here, and we wish them the best and good luck in the future.
Thank you.
Thank you.
Thank you.
Oh, I think
You're muted, Dr. Cornelius.
you're muted. No, well.
Dennis, you're muted.
All right, so thank you again, gentlemen. We'll make way now for our contingency cutoff tool team. You can go ahead and start loading up here. I'll stop share and go ahead and pull up your presentation. And again, unfortunately, I was muted, but I want to thank again the representatives from Lamb Weston for their kind and generous and time intensive commitment to supporting this team and our program in senior design. Very appreciated.
All right, can y'all hear me?
So how are you looking there? You got your whole team on board? How's everybody checking in?
Can you hear me?
Yep.
I hear you.
All right.
Mic check.
Yep.
Good to go?
Mic
All
check.
right.
Yep, Elijah.
All right.
you're here.
We'll give it, I want to thank you for putting this together and being prompt. We appreciate the opportunity to hear from you on this project funded from One Subsea Systems in South Louisiana. They're a Schlumberger company. Men, it is all yours. Take it away.
All right. Thank you. Good afternoon. We are the One Subsea Contingency Cutting Tool Design Team. Our team members are Elijah Stedman, Luke Morrow, Joseph Harrison, and Brian Higgins, all of whom are mechanical engineering seniors at Louisiana Tech University. Today, we'll be walking through some general project information, an overview of the problem that inspired this project, the design of the cutting tool, an analysis of said cutting tool, the design of our test fixture, and we'll wrap up with our conclusions and open the floor to any questions you may have. First, a little information about OneSubsea. OneSubsea is a company that delivers integrated solutions, products, systems, and services for the subsea oil and gas market. Our industry sponsor is Casey Torrey. Casey is a mechanical engineering alum of Louisiana Tech University, and he's in the call right now. Next, some important initialisms we'll be using during this presentation. OCSV is the OneSubsea Clamping System Vertical. ROV stands for Remotely Operated Vehicle. And P and ID stands for Piping and Instrumentation Diagram. Now, we'll move into a broad overview of this project. 7,500 feet below sea level, the ambient pressure is about 3,500 psi, and the temperature is approximately 34 degrees Fahrenheit. And it is the concern of Schlumberger that after 2 decades of use at the seafloor, calcareous deposits may develop and prevent the removal of the OCSV from an oil well. This would be financially untenable for Schlumberger. Now, there are 3 primary areas of challenge in this project. The first being the material of the lead screw we need to cut. It's made of nickel 718, or Inconel. Inconel is considered one of the most difficult materials to machine due to becoming both stronger and harder as it's worked. On top of that, this cut must be completed in under 2 hours as per the constraints given to us by OneSubsea. Second, the tool needs to be simple enough such that it is operable by an ROV. Third, we must design and prototype a test stand that mimics the dimensions of the OCSV intervention window. In this image, we have arrows calling out the ROV, the OCSV, and the lead screw. And this is just to provide a visual to go along with what we'll be discussing today. But for now, let's zoom into the OCSV. In image 1, we have the fully assembled OCSV. And then from image 1 to 2, we eliminate some of the extraneous components, leaving us with the top plate, lead screw, and clamp mechanism called out. In image 3, we've removed the top plate assembly to reveal the target of our cutting process. We also see how the clamp operates. By turning the lead screw clockwise or counterclockwise, the clamp opens or closes. The OCSV, which we see here, is a proprietary clamping system that allows for controlled oil flow from a deep sea oil well to a surface side oil rig. The process shown here is the method of installation for the OCSV. The OCSV is guided to the oil wellhead by the ROV, and the fluted portion at the bottom ensures the OCSV lands where it needs to. From there, the ROV uses a hydraulically powered torque tool to turn the lead screw and engage the clamp, which in turn creates a powerful seal. In these images is our ultimate goal with this project. In the case of binding between the lead screw and the clamp mechanism, our tool will be deployed to liberate the OCSV from the oil well. Now that I've explained the issue we're facing and how we'll address it, I'd like to explain in a broader context why this tool needs to be made. A phrase we've been reminded of during our project is out of an abundance of caution. And I would like each of you to keep this phrase in mind as well as we go throughout this project. This class of tool is to be used in cases of catastrophic failure or unexpected drops in oil prices, or in case corporate negotiations fall through. And now, I'd like to hand off to Luke Morrow to discuss our cutting tool design. Luke?
All right, guys. Before I kind of talk about the tool itself, I'd like to talk about the considerations. So obviously, as we said before, it needs to be controlled by an ROV. There's hydraulics on board, so that is a big thing. Also, it has to be high power because it needs to cut through a lead screw, and the Inconel lead screw, and it needs to satisfy geometrical constraints. The first consideration was the hydraulic shear. We liked this design because it was simple, easy to implement, and it was fast. However, due to some constraints, we threw this design out of the window. The next one was the reciprocating saw. The reciprocating saw was also simple, but due to vibrations and Inconel properties, we threw this one out of the window as well. The next one was the accelerated corrosion. Accelerated corrosion was cool, and we looked into it for a while. However, due to there being electrical components on the OCSV, this was also thrown out. Finally, we got to the circular saw. Circular saw was the design that we ended up going with because it satisfied the Inconel's cutting properties, and it also was not complicated to implement. I first want to kind of bring y'all to some of the original designs that we had to talk y'all through the process that we went through. On the left image, you can see we have sort of a linear saw the ROV would operate to push into the Inconel lead screw. The next, we decided to go to the middle image, which was more or less what we kind of used, is it mounts onto the OCSV, and then a hydraulic cylinder would push the saw into the Inconel lead screw. The right image did a similar thing, except it mounts on top of the OCSV instead of on the bottom. That brings me to our final design. This design was chosen after much thought and headache. We finally decided to go with it. So I want to go into the components that go into this tool. First, you can see the keyway and the keyway interface. So that eliminated most of the degrees of freedom, but not all of the degrees of freedom for this tool. So we decided to interface with the legs using the legs interface. This eliminated the entire degree of freedom and ultimately gave us a base to operate off of. Now we can talk about the pivot point and the swing arm assembly. If you look at the handle is what the ROV would push to actually push the saw into the lead screw. I want to kind of show y'all how this works in coming images. If you look at the image on the left, you can see the inboard hub called out. The inboard hub is something we do not want to damage. However, we want to cut all the way through the lead screw mount. This will release the clamp. Our pivot was specifically placed so that it does not hit the inboard hub, but it does cut all the way through the lead screw as seen in the right image. I want to show y'all a quick animation. Hopefully it's clear and not choppy for you guys. That describes a theoretical deployment of this tool and cut all the way through. So as you can see, this is a theoretical deployment of the ROV placing our tool onto the OCSV. Now eliminate all degrees of freedom, allowing the ROV to push the saw, cutting all the way through the lead screw. Now I want to bring you on to some saw shaft components. I want to talk about the bearing, the shaft, and the coupler mostly, because those are some things we'll be talking about shortly. Overall, these components were designed to transmit torque from the motor to the saw. I now want to talk about our hydraulic system that we use. So we used a 4-way, 3-position spool valve. As you can see in the image, it's a tall stack of different orientations. The middle orientation is neutral, which you see now. It allows the hydraulic supply to be on, but the motor is not rotating, or the saw is not rotating. However, the image you see here, the hydraulic valve is in the forward position, allowing the hydraulic supply to supply power to the motor, allowing it to transmit torque. And you can see the pressure gauge there. We will talk about that in coming slides. I now want to pass it off to Elijah Stedman.
All right, guys, now I'm going to talk to you about some of the design analysis that got us to where we are now. So first, we're going to talk about the variables that we use in the hydraulic calculations. First, we use Q is flow rate, D is the inner diameter of the hose, DT is the displacement rate, P1 is the inlet pressure read by the pressure gauge. So the first calculation we did was a fluid velocity calculation, which we found to be 16.43 feet per second, which was used to size all the hoses in the hydraulic system. Next up, we did a motor torque calculation, which we found to be 36 foot-pounds. We used the pressure gauge to find the pressure in that calculation. Next, we did a motor RPM calculation, which we found to be 385 RPMs. Through the research that we did, we found that cutting Inconel, your RPM should be low, which we found to be below 450. Next, we did some shaft calculations. So the critical speed calculation we did was 9,861 RPMs. We did this calculation to make sure that we weren't reaching the resonant frequency and our tool would fail. Next, we did our bearing life calculation, which we found to be 3,766 hours. We know that the tool can only be down there for 2 hours per Schlumberger's recommendation. So we know that the 3,766 hour life is plenty of time. Lastly, we did our maximum deflection calculation. So we used a force of 200 pounds and a torque of 50 foot-pounds. So as we showed you before, the torque that we calculated was only 36 foot-pounds. We used the 50 foot-pounds to be conservative, and we still only found a maximum deflection of 0.2 thousandths of an inch. All right, now we're gonna get into some of the safety measures we used when testing this tool. So on the iron worker, there's an emergency shutoff switch. And basically what we needed was another person to hold on to that so that the fluid would flow through the system at all times, and another person pushing onto the saw to make it go. We also had on our valve an internal pressure relief function, which basically stopped the pressure in the system from exceeding the value that we set it at. And we also had redundant hydraulic switching. So basically we had a valve on our tool to turn on the flow to flow through, and we had another valve on the iron worker to allow the flow to flow through. And lastly, all members of the team wore proper PPE. Okay, now we're going to talk about the testing cut data. So we did 5 test cuts lasting 1 minute each. They were all pulsing cuts, 4 seconds on, 2 seconds off. The reason we did that was to simulate the cooling that was found at the ocean floor. Basically, after we did this, we found that every minute we were taking off 1/8 of an inch, which gave us an estimated time to cut completely through the lead screw of around 30 minutes, which is well below the 2 hours that Schlumberger said we should reach for. And now I'm going to introduce you guys to the Turtle, the thrust utilizing removal tool for lead screw extrication, shown on the right. And now I'm going to hand you guys over to Brian Higgins to wrap things up.
All right, guys. I'd now like to switch gears and bring your attention to our second deliverable, the OCSV test fixture. Now, before I reveal our design, let's first discuss some of the constraints and considerations that were made when developing our design. The most critical of these is that our test fixture accurately mimics the critical dimensions of the OCSV. The design also needed to be simple to manufacture as well as affordable. It was important not to detract from our tool's budget. Finally, it needed to be robust enough to handle the weight and loads applied by the cutoff tool, but light enough that we were able to transport it and assemble it with ease. Next, I'd like to speak about some of the key components that needed to be emulated by the test fixture. The image on the left is of the OCSV that was seen earlier. If we zoom in, there are 6 major components that our design needed to include: the keyway, top plate, legs, bottom plate, inboard hub, and the 3-piece.
Hey, Brian, could you take a moment and check your connection there? We're having you drop out occasionally.
My voice or my video connection?
I didn't see you dropping out, Brian.
Okay.
Yeah, continue. You're fine.
All right, so now let's take a look at some.
Try again, Brian.
You can go to the next one, Luke. The design you see here was a late iteration that we devised. As you can see, all the major components are there. Many are clearly emulated. However, we had to think outside the box when mimicking the 3-piece clamp. We met with our sponsor and decided that it was unnecessary to recreate the clamp itself. So we designed a simple mount that represents the gap the saw must clear in order to cut the lead screw. While this iteration met several requirements, we found it to be far too expensive, heavy, and difficult to manufacture. We had to continue iterating to find a better solution, which brings me to our final design. Our final test fixture design still includes all the critical dimensions and components required to properly emulate the OCSV. However, rather than 2 to 2.5 inch thick steel plate, we broke it down into sub-assemblies consisting of 1/4 inch plate that we welded together and assembled with a combination of 1/2 inch bolts and spacers that made it far easier to fabricate. This allowed us to keep the weight down and deliver a test fixture that didn't break the bank while still meeting our critical dimensions. Now here are some actual images taken of our completed test fixture prototype. Now that we've shown you our tool and test fixture, here's a short clip of Luke demonstrating just how easy it is to install and use. At this time, I'd like to start wrapping things up with a quick look at our budget before bringing us to a close. To put things in perspective, Schlumberger has been designing a similar tool in tandem for the past year, and it cost them upwards of $200,000 to engineer and prototype. Now, looking at our budget, Schlumberger allotted us $3,080 to design our prototype. Our team spent $1,955 designing and fabricating the cutoff tool and test fixture, with the bulk of that spent on the hydraulic components and the steel we use to fabricate. I'd like to take a moment to expand on this, as I'm very proud of what our team has accomplished. We were able to keep our costs well below budget by doing all the fabrication ourselves with the guidance and help of our machine shop foreman, Neil Reinhardt, as well as our friends that work in the Proto Lab. We utilized Tech's machine shop to its fullest, employing the water jet and plasma table to cut our 1/4 inch and 1/8 inch plates. We utilized the CNC mill to fabricate our bearing housing and motor mount, as well as wood routers and the thingery to construct jigs that significantly simplified all of the welding that we had to do. All of our hard work allowed us to deliver this project on time and under budget. Our tool successfully interfaces with the test fixture, which met all the critical dimensions and effectively emulated the OCSV. We were also able to deliver a project cut time of around 30 minutes, as Elijah mentioned earlier, which we were very proud of considering the Schlumberger defined success for us as less than 2-hour cut time. Now to bring things to a close. We recommended that the remainder of our budget be used to implement 4 major upgrades and improvements to our design. First would be to install handles and guards to ensure easy maneuvering and safer operation. Second is to improve the efficiency and operation of the hydraulic systems by resizing the motor and the lines for better performance. Third would be to apply protective coating to the tool and test fixture to make sure there was no corrosion after sitting outside or being used in water. And finally, we would like to extend the cutting arm to increase the moment applied when cutting in order to multiply our cutting force. With that, I'd like to close by thanking our sponsors at Schlumberger, Casey Torrey and Justin Sawyer, our faculty advisor, Dr. Swanbaum, and Dr. Cardenas for leading all the Mean 480 students during these troubling times. And finally, all of you on the advisory board and at home for taking the time to listen to our presentation. I'd now like to open the floor for any questions.
Go right ahead, Council, and anybody else wants to join in on the chat, be free to do so.
Hey guys, this is Matt Wallace on the council. I noticed in the presentation y'all didn't do any SolidWorks analysis, or didn't show that you did. Did you do any engineering analysis like SolidWorks or anything like that?
You mean like FEA analysis?
Yes, exactly.
Luke, you want to take that one?
We did do some FEA analysis. A lot of this geometry is hard to do calculation on, as you can see, but we made sure most of these components are designed to where if they are hit or bumped, they're not going to deflect much at all. So most of the components didn't need much analysis because they were over-designed. We did do an FEA on the shaft deflection, as you saw. That was just to make sure that our saw was going, that was the fail point for our saw, and we wanted to make sure it was rigid enough to make sure the saw didn't deflect much during our cuts.
Sounds good. Thanks. Y'all did a good job. Impressive.
Thank you.
Hey guys, this is Evan Sanders. Yeah, it's a pretty impressive project. One question that I had was, obviously this would be hard to simulate, but you know, this thing's supposed to perform at sea floor level. And so, you know, what type of issues do you think this thing might have under that type of pressure in that, you know, saltwater environment type deal?
So something that we learned during this project was about the hydraulic systems on board of an ROV. And that was kind of our first major concern because, you know, when you get that deep, you've got a lot of hydrostatic pressure. What's really neat is there's systems on board the ROV to compensate for the pressure outside. And so that was one thing we learned pretty quick that simplified this. You know, we didn't have to overbuild our hydraulic system in order to meet those pressures. The other thing we had to keep in mind was to not build any pressure vessels on accident. You know, so all of those handles or pieces of tubing couldn't be capped in any way, because if they were sealed, they would just crush as you got deeper. And then, with salt water, of course, we're using carbon steel, so we'd have to do either some sort of cladding or protective paint, which Schlumberger uses a lot of that. So we just kind of relied pretty heavily on our contacts at Schlumberger to get advice on, how to avoid things like that.
Great, thank you. Thank you for taking those considerations and kind of looking into all that stuff. Good job.
Thank you.
Hey guys, Justin Bounds with the Advisory Council. I guess one question I've got is, since you'll be using the ROV to install this cutter into the keyway, how can you be confident that the cutter has made it all the way to the back of the keyway and that something's not lodged in between, like a fish or some sunken treasure or things like that?
Yeah, so and I think Luke, you can add to this, but the idea, if you see that the head there that I'm welding on, the way we designed that was so that the dimensions of that piece were to fit into that keyway in such a way that it would lock down in place. And if there was anything in the way, we tried to build it robustly enough to knock out any kind of, maybe coral or buildup. But the way we designed it was so that it would punch through anything in that keyway, and once it's completely flush with the top, that top plate is completely flush, then it's in place, and then it can rest on those legs. And I mean, Luke stood on top of this thing, and we jumped, not jumped around on it, but we moved it around and different things, and it's actually extremely sturdy. But Luke, do you have anything you want to add?
Yeah, so I think I understand your question, and part of the way that they're going to make sure that this tool is properly in place and the lead screw is cut all the way through in the end, there are, I believe, 7 cameras on the ROV, so they will be able to see it. So that's one thing, but we did design, as Brian was saying, we designed a whole bunch of wedges into this thing and the tolerances to make sure that if there was anything in the way, the tool would work its way into the keyway.
And that's a good picture right there that you can kind of see. Yeah, some of those.
Okay, thanks.
Thank you.
Hey guys, this is Sam with the Advisory Council. So you guys rolled out using a hydraulic shear. What was that reasoning?
So it was the geometric constraints that basically stopped us from being able to build up enough material to shear the thing without breaking the tool itself.
Yeah,
we would have kind of were restricted by your, it has this, I guess, the constraints of the lead screw itself. Is that what you're saying there?
Well, so in order to shear the lead screw, we would have needed to put a truly astronomical amount of pressure or force, pressure in this case, I guess, on this lead screw. And I don't have those calculations quite memorized, but we also determined that in order to shear through Inconel, the only material we had access to budget-wise would have been steel, and the bulk amount of steel required to survive shearing Inconel would have been more than can fit. You can see it just in that last picture. Can fit between the Inconel bolt and the
clamping mechanism.
Exactly. Yeah.
Only about like a 2-inch space. So
right. Yeah. So we would have needed a great deal of steel behind it as well to support the shearing process.
Right. Understood. I might would maybe show that in your report or something. I know that shears are used a lot in this industry.
Right. Yes,
for
sir.
things of that depth. So you're using this cutting tool. I mean, what's your saw blade? Does it have like a diamond bit, or were you Schlumberger like say, hey, this is what we want to use kind of thing? Or
surprising.
Yeah, well, so a lot of it was the price, but I did some research into recommendations for cutting specifically Inconel. Luckily, we had a resource. It's advanced methods of metal machining, something like that, and they describe the most recommended way to cut Inconel, and that's if using a circular saw, which we are, a cold saw. It's best to try and use. It can be any tungsten carbide saw blade, but the most important thing is actually the geometry of the teeth of the saw. They need to have a forward aggressive rake angle. The cut is going to be pretty slow, like that's why our RPM is so low, and you're just going to have to really work through it with excessive cooling. And that's very similar to what we ended up doing. We couldn't find a 14-inch saw blade at a reasonable price point with an aggressive rake angle. So what you see here, it's actually got a negative rake angle, which still works. It's just not quite as effective as it could be. So that's sort of how we went about deciding the saw blade type.
Right, understood.
Adding on to that a little bit, that was something that we planned on experimenting a lot with, was different angles and different types of blades and things like that. We had some money left over that we were planning on buying a few saw blades and trying them out, but due to some of the restrictions we had with the pandemic, we didn't get to do it.
Yeah, no, it's a beautiful prototype, guys. It's some very nice handiwork. So obviously there's some things you can do, going forward with this project. They wanted to pass that on to another group, later years or something. But anyway, great work, guys. It's awesome.
Thank you.
Thank you.
We appreciate the feedback.
Hey, all guys. Right, we need to make room for, I see Mr. Torrey, though. Mr. Torrey, if you could give us a minute of your thoughts, and we'll need to make room for the next team. Go ahead.
Yeah, I'll be quick here. Hey, guys, great job, great presentation. Really proud of you guys. I think overall, you took all of our design considerations and tried to put them into this project. I guess from the design council's questions, some good questions there. Some of the things that you asked around how does hydrostatic head affect the tool? At OneSubsea, we're going to actually put the tool in a hyperbaric chamber to simulate how does the tool respond at depth, which obviously you can't do in a university setting, but we can in a production setting. And then we also drop test the tool to represent, hey, what happens if the ROV drops the tool? How will the tool break? So those are some of the things that are different from a university setting to production. But overall, great job, and had a really good time this year working with you guys. So keep it up, and good luck in your future endeavors.
Thank you so much. We had a blast.
Thank you, Casey.
Thank you, Mr. Torrey. All right, guys, we'll let you move aside and make room for our final presenter of the day. We thank you very much. And now we're going to call up our turbine distress simulation tool, folks. And let's get you ready to share.
Hello.
Hey, how's it going? You guys ready to load up?
Yes, sir. All right. Can you see my screen?
Yep, you're coming in great.
Wonderful. Hi, everybody. My name is Abigail Walker.
I'm Ryan Schaefer. I'm Andrew Madrid.
And we are the Turbine Distress Simulation Tool team. Welcome to our capstone presentation. We are sponsored by Bentley Nevada, a Baker Hughes company, and special thank you to our faculty advisor, Dr. Crittenden. First, we'll go through our introduction with some of the problem statement. This is our sponsor, Mr. Michael Titone. He graduated from Tech here. He works with Bentley Nevada out of Vicksburg, Mississippi. He travels all over the area, teaching operators how to diagnose different problems with turbines and other rotor systems. Bentley Nevada is an industry leader in asset condition monitoring, and they have about 6 million sensors deployed worldwide that they use to monitor turbines and other rotor systems. This is our Bentley Nevada rotor kit, the RK4. We have multiple ways that we can balance this and reconfigure this. You can see the holes along there, along the side of the trough, help with that. This actually simulates a real turbine. The rotor is only about 10 millimeters in diameter, whereas a real turbine would be about 2 feet. And the rotor here is actually a lot more flexible than a real rotor would be. Next, let's go into some of the theory. This is the Newkirk effect. The Newkirk effect is actually a vibration change in the rotor due to thermal distortion, which basically means one part of the rotor is heating up and the rest of it is not, which causes some bow that we'll talk about in a minute. This can be caused by going through a critical speed, which causes the rotor to vibrate way more than normal, and it rubs against a seal that normally would not be touching it. So Ryan is going to talk some more about this.
Let's talk a little bit more about the theory that causes unbalance. So in any rotary system, if there's a misalignment or if there's a off-center mass, you're going to get some imbalance, and that can cause a bow. Here on the left, you can see a cross section of a rotor. It's rotating counterclockwise. It's denoted by the omega. The center is denoted by the black dot and the O. Here you can see there's an imbalance, also called a heavy spot in yellow. And when the rotor is rotating, you're going to get a force in the direction of this imbalance. Due to damping in the system, the actual rotor's response, or bow, will lag this force in the direction opposite of rotation by some amount, and we call that the phase lag, which is denoted by alpha. The rotor's response, shown in blue, produces a high spot, and that's actually the spot that we can measure on the rotor as it rotates around. And so before the first critical speed of the rotor, the bow behavior is going to resemble what you see there in the bottom of the slide. Critical speed is simply an area where the rotor's vibration starts hitting its natural material resonance, and so you'll get a much higher vibrational amplitude than you would normally experience. But for the purpose of this project, we're only concerned with up to and before the first critical speed. So the rotor's bow is always going to resemble this jump rope effect with the high spot always facing out as it rotates around. Next up, we're going to talk about a little bit of the frictional effects. These bowed rotors have the opportunity to rub on some stationary components like Abby mentioned. One such of these components is the seal. The high spot of the rotor will actually contact the seal and create a frictional force that will heat the high spot up in one specific location. This creates a temperature gradient where the high spot is hot and the other side of the rotor is cold, which actually cause a thermal warp in the direction of this hot area. So when we combine these two effects, we get the Newkirk effect. First off, like we mentioned before, you have a heavy spot and the rotor is experiencing a force FUN in the direction of that heavy spot. The actual rotor bow lags the force by some angle alpha and you get a high spot. The high spot rubs on the outside surface of the seal and it heats and you get a thermal force in the direction of this hot spot. And then the thermal force and the unbalanced force add together and actually move the heavy spot and the high spot over because they're adding vectorially. These forces are just adding together. And what you end up with is the high spot moving in the direction opposite rotation. And so this cycle continues. That new high spot will rub on the outside surface of a seal or something else again and continue to heat up. And so the Newkirk effect can be described by an increase in bow or vibrational amplitude, as seen by the distance from the center of that circle on the left, and a changing location of the high spot or phase angle. And this change only happens in the direction opposite of rotation, as you can see. In this case, it'll be clockwise since our rotor is rotating counterclockwise.
Now let's talk a little bit about some project requirements. We would like to recreate this high spot and rub on the rotor kit. We need to create 2 different attachments for our sponsor to be able to test after our design work here is done. We need to be able to reproduce this, so we need to have some detailed shop drawings. We need to be able to test a variety of different inserts for the rub attachment, and we also need to prioritize ease of use. Some constraints, first off, budgetary constraints. We'd like to keep this under $1,000 to reproduce. We don't need to damage the rotor in any way, shape, or form. We need to keep the critical speed greater than 3,600 RPM. We need to try to emulate tolerances and clearances found in actual turbines. So we're trying to keep to about 0.010 of an inch of clearance. And we also want to keep it balanceable, relocationable, and removable. So a little bit of the design selection that we considered. First, we wanted to see what was currently being used on the rotor kit. Currently they're using what's called the rub screw attachment. And we liked this for a few reasons. It was very user-friendly and it didn't damage the shaft due to the materials chosen, but it did have some drawbacks. There was low contact area, which resulted in negligible heating on the rotor itself. Some discarded conceptual designs that we looked at, we wanted to either rub on the mast disc itself or use a larger rotor. And we ended up throwing these out due to cost, but they did offer great benefits as it increased the surface velocity where it would be rubbing. The accepted conceptual designs that we decided to move forward with was a larger contact area on the original rotor and a hollow pipe attachment that would increase the diameter of the rotor in a selected area. Here you can see how we weighted each of these concepts. And as you can see here, user friendliness was weighted pretty heavily. The larger contact area and the hollow pipe attachment were selected to move forward, and the mast disc and larger rotor were rejected.
Next, we're going to talk a little bit about our final designs and their iterations. This is our 10 millimeter attachment, one of our 2 designs. It utilizes our existing rotor, which was the 10 millimeter rotor I talked about earlier. It's very user-friendly because all you have to do is screw down that screw and then the carriage assembly is engaged. It's simple, it's easy to install on the rotor kit. It only takes about 5 minutes, as you'll see later, and it's only about $300 in production cost. We want to dive a little bit deeper into that carriage subassembly to show you some more about how it works. So we can actually put multiple rub attachments on here to emulate a real turbine seal, which would normally have multiple spikes along it. We also have bronze fittings here that are press fit into the inside of that carriage subassembly, as you can see here in the green circle. We have those press fit, and then they ride along linear rods to go up or down. This is our second design. This is the pipe sleeve attachment design. This is a little bit similar to the other one in that the bracket is pretty much the same, but we really wanted to grow that rotor a little bit artificially, sort of. We put that pipe sleeve on there with the mass disc and a couple of couplers, and we actually used pretty much the same bracket design to engage. This increases the surface velocity of the rotor, which gives us about 7 times the surface speed. It increases the critical speed due to the stiffness and adds mass to the system. It's very user-friendly because, like I said, it uses that other design pretty much, and it is also under the $1,000 production cost. This is our project budget that we were given by the school. We were given about $2,200, and we stayed about $350 under budget. We would have saved a lot more. Unfortunately, due to the pandemic, we had to outsource a lot of our machining to a place that charged $100 an hour instead of $30 an hour. But we still stayed pretty well under budget. Some of the economics of our team, we saved Bentley, Nevada about $16,000 all in all, and we added value to their class that they normally teach, and that we were teaching operators how to better diagnose issues with turbine systems, which indirectly reduces the outage time for turbines and increases power availability to consumers.
Now I'm going to walk you through some of the engineering analyses that we used to design these parts. First, for spring selection, we wanted to have springs that would be able to fit over the linear rods. We wanted to minimize the spring constant as to minimize the force needed to compress these springs. And we also wanted a factor of safety greater than 2 against buckling. We wanted this factor of safety against buckling to increase the stiffness in the system. We didn't want any play or anything like that, since we are measuring very small changes in the system. As you can see here at the bottom of the screen, this formula was used to find the critical length that the springs could be compressed before buckling. And as you see here in the upper right-hand corner, the smaller rub attachment does not buckle, and the larger rub attachment has a factor of safety against buckling of 4. And this is due to the amount that it travels versus how much it can be compressed before buckling. For interference fits, we wanted to do an interference fit on the bushings going into the carriage, as well as the steel rods going into this lower bracket. As you can see, using the tolerances here, we got a max stress of 178 megapascals on the carriage assembly, which is less than the bronze and the aluminum's yielding strength. And we got a max stress of 77 megapascals on the lower bracket, which is less than the stainless steel and the aluminum's yielding stress. This lower stress results in no permanent deformation on our system. We also needed to find the critical speed of the rotor itself. And to do this, we used Shigley's mechanical engineering design concepts, and we represented our rotor as a simply supported beam shown in the upper right-hand corner. To do this, the first step, we had to take any excess masses that would be on the rotor and lump them together at the center. Then we found the critical speed of just those masses on a rotor of negligible weight, and we found the critical speed of that. We found the critical speed of the rotor itself, and then in step 3, we combined them all together to find the overall critical speed. We then took this data and plotted it against different lengths of our rotor, and as you can see here, we can still keep a rotor length of about 330 millimeters and still stay above our 3,600 RPM. We were actually able to test this on our rotor itself, and we were able to find that the data was really representative of what we can see on the rotor kit. Here you can see it implemented on our rotor kit. This is the smaller attachment implemented. For the pipe sleeve, we also had to find a critical speed, and this one was a little bit more complicated due to the geometry. To do this, we had to outsource to a paper that we found through our sponsor. And in this paper, they broke up complex shapes such as this into different sections and summed the critical speeds of each section to find a overall critical speed. So we did a very similar thing here. You can see the different sections subdivided. And doing this, we got a critical speed of about 5,000 RPM. We can reduce this by reducing the length of the pipe itself, which we'll probably end up doing in the future.
Next up, let's talk about a little of the performance evaluation we did on our 10mm attachment. First up, we did assembly time. We had a member of our team assemble the 10mm attachment onto the rotor kit in the previous configuration where the bearings are no further than 330 millimeters apart. We did this 5 times. Over the course of our assembly trials, we noticed that the time it took to assemble went down and started leveling off around 5 minutes. And so from this, we recommend that whoever is teaching the machinery diagnostics class take about a 5-minute break to be able to actually put the attachment on our kit. We also recommend that the operator practice the assembly at least 3 times before teaching the class. Next up, we're going to talk a little bit about our rub test. For the rub test, we use several different inserts so we could try as many different things as possible. 3 of the ones are shown here. We have a brass one with 5.50 millimeter radius, an aluminum one with 5.25 millimeter inner radius, and then another brass one with a 5.0 millimeter radius. This corresponds to about a 20 thousandths of an inch, 10 thousandths of an inch, and 0-inch tolerance with the rotor. First up, we're going to talk about our brass 5.50 millimeter rub test. On the left here, you see a figure just to remind you of how the polar plots are set up. We again have proximity sensors positioned in the X and Y axis. The rotor is rotating counterclockwise, denoted by the omega yet again. And the amplitude, or the amount of bow, is denoted by the position relative to the center. And the location of the high spot is denoted by the angular location along the plot. On the right is a plot produced by Adre, which is Bentley Nevada's proprietary analysis software. Here you see the ramp up and ramp down vibration behavior, which just means as we're speeding the motor up and slowing it down, that's just the vibration that it detected. During our actual rub test, we have the data circled. It's a big noisy clump of data and a lot of interesting things in there. So we decided to analyze the components. The 2 components of the vibration are amplitude and phase. In this case, amplitude is measured in mil-pp, which is thousandths of an inch peak-to-peak amplitude. The test took place over 25 minutes, so that's our bottom axis. And the phase angle is measured in degrees, which again, that's just the location of the high spot. So at the start of our test, we were at between 12.5 and 13 thousandths of an inch of vibration. And over the course of our test, we oscillated vibration up and down, but it really remained around the same level. And you can see the error bars are overlapping, so there really wasn't a significant increase in amplitude throughout the course of the test. The phase angle dropped sharply over the first 10 minutes of our testing, and over the remainder of the test rose back up towards the initial value and averaged out around 345 degrees there. But you can see the error bars are rather large, and so there's not really a significant difference there either. And from what we can see from the phase angle graph is that all the changes were in the direction of rotation, and the Newkirk effect describes phase shift in the direction opposite rotation. So we can't really say that the Newkirk effect actually happened during this test. Next up, we have the 5.25 millimeter rub test. This was on an aluminum insert. We don't have the ramp up behavior here, but we do show the ramp down. But the most important part is all that noisy data in the big circle there you see. So at the beginning of the test, similar setup, at the beginning of the test, we had 26 thousandths of an inch of vibration. And over the next 10 minutes, it rose up to 36 thousandths of an inch of vibration and kind of leveled out there. And so this is a pretty significant increase in vibrational amplitude. And we were very happy to see that. But when you look over at the phase diagram, you notice over the first 2.5 minutes, the phase angle shifted from 94 degrees down to about 83 degrees. And throughout the course of the test, rose back up towards that initial value, leveling off around 92 degrees. Again, we don't really see any significant trend in the direction opposite of rotation. So we, again, can't say that the Newkirk effect was satisfied here. Our third test was the brass 5.0 millimeter rub test. This one was a little bit different because there is no clearance between the insert and the actual rotor. And so we noticed some really odd behavior. You can see that the plot on the right looks very different from the previous 2. And so here again, we broke it up into components of amplitude and phase. At the beginning of our test, we were vibrating around 32 mils of amplitude, and immediately it dropped by almost half over the first 2.5 minutes. And over the course of the test, the amplitude continued to slowly increase and approach that original value, leveling off somewhere around 29 thousandths of an inch of vibration. The phase angle showed very similar behavior. We started at about 4 degrees phase angle, and that went in the direction of rotation by about 15 degrees and rose up back towards the initial position. This is very odd behavior. We believe that this is due to the insert actually constraining the rotor, and as it was rotating, the rotor was taking material off of the insert and returning to its original position. We don't really recommend that the brass 5.0 millimeter rub test is used because of this, because it's actually not allowing the rotor to rotate and behave in the manner that it's supposed to. We also noticed some qualitative results. First of all, the inserts were water jet here at Tech, and before the test, they all have very rough water jet finish along the inner surface that the rotor rubbed on. After the test, the entire inner surface was polished, and from this, we know that the rotor made contact with the entire inner surface of that insert. We were very happy to hear this because one of the problems with the rub screw was that there was very minor contact area, and so we improved this into a full 180-degree sweep. Next up, we know that we produced a high spot and that the high spot was the only location that rubbed, because as you see in the figure on the right, we marked the rotor up with Sharpie before the test, and the area where the Sharpie was rubbed off after the test was the area that rubbed. And so from this, only a small section of the rotor actually made contact with the inserts, and we know that we produced high spot rubbing. There were also a few bad observations we noticed. For example, the aluminum inserts actually galled, or a little bit of material got stuck to the shaft during the rotor during the test. This was very bad behavior because it was very difficult to remove the aluminum from the rotor after the test, and so we don't recommend aluminum's used. The brass had no problems, they just simply abraded material away. Also, we noticed there wasn't really any significant heating at that high spot after the test. The bearings on the rotor kit got fairly warm, and so we think some of the amplitude increase might have been due to that because that was adding thermal energy to the system. But the actual high spot itself wasn't significantly hotter than any other part on the rotor where it was rubbing at.
So I think we're ready to wrap up with some conclusions and recommendations. To conclude, all of the rub tests showed that desirable partial rub, but none of them showed the Newkirk effect or the thermal movement behavior that we were really trying to emulate. Unfortunately, the aluminum insert galled on the rotor, but the brass inserts did not. Due to all this, we recommend the operator practice at least 3 times before they actually try this out in a class setting, and whenever they try this out in a class setting, to take a 5-minute break for all the students to leave the room so that they can put everything together. We also suggest that the aluminum rub attachment not be used due to the galling. We don't suggest for the 5.0 rub attachment to be used because of that damping that it added to the system. We also suggest that the inserts be replaced after extended use. For some future design iterations, we recommend to our sponsor to try an interference fit with a slit fit to replace that interference fit with a slit fit for the rods. We actually tried this out on our pipe sleeve design. It worked great. We also recommend cutting the pipe sleeve design down to a smaller size to reduce that mass. Whenever we ran this in person, it was kind of scary how much it was vibrating whenever it ran up to speed. So that would possibly decrease that. We also recommend researching different materials for the rub inserts to maybe increase that frictional coefficient and to possibly investigate a larger rotor diameter option. Does anybody have any questions?
But I will shut us down very strictly at 5 o'clock because our judges have a terrible task before them. And but first things first, go ahead with your questions.
Well, I think we're up for the terrible task. We'll take a shot at it. First off, good job on the project and the presentation. One question that I do have is, were you able to compare any data from Bentley, Nevada's existing setup to the test setup that y'all came up with?
Okay, so I'll answer that question. So when we actually used that rub screw, there really wasn't any change at all in the signal. I remember you saw in the polar plots that we presented earlier that there was a big noisy clump of data where you could see that it was actually changing. But we tried the same thing with the rub screw, and there just wasn't any change at all. So we know that we were getting some more behavior out of the attachment we designed, but unfortunately still didn't produce the Newkirk effect like we wanted it to. We did achieve the partial rubbing though.
Okay, thank you.
All right, so if you're just joining us, we're deferring to the council for verbal questions. Any other questions we'd love to engage, we'd recommend using the chat feature. And we'll just hold for a couple more questions here since we have the time.
Hey guys, this was Evan Sanders with the council. One question I have for you, you guys did a lot of great analysis on this, a lot of great data analysis and engineering looking into this stuff. What was the biggest takeaway from that, from just the numbers themselves, and what do you recommend from those things? What was probably, like, I guess, a surprising finding from that?
Critical speeds matched
Yeah.
up.
Yeah, so we were actually pretty thrilled that the critical speeds on the actual rotor matched up very closely with our actual calculation there. When we actually tested on the rotor kit, I think we were maybe like 50 RPM off, and it was just really neat to see that the actual book calculations matched up so well with the real system. As far as the rub testing, we really think that the smaller like 10 millimeter rotor wasn't producing enough, or didn't have enough surface speed to produce enough heat in one single location. And actually just recently we have done some more testing on the pipe sleeve, and we were able to see that the spot that was rubbing was actually significantly heating. So we definitely recommend having something with a larger area, and so that it has that more surface speed. And I think that's probably the biggest takeaway, is that just that 10 millimeter rotor is probably too small and wicks the heat away too quickly to actually produce a hot spot and get a thermal bow out of it.
I do have something to add to that, actually. Keep in mind that a real turbine rotor is about 2 feet in diameter, and we're trying to emulate this on a 10 millimeter rotor diameter. So it's much, much decreased from a real turbine.
Yeah, that's great. I was just interested to see what you guys have learned from that, because you can do all the analysis, but the important thing is what you get out of it. So I'm glad to hear that you guys did. So good job.
Okay, if I add a few comments now?
Please do, Mr. Titone. Thank you. Mr. Titone's the sponsor representative with Baker Hughes.
All right, I just wanted to say that I'm really pleased with what the team did. We didn't accomplish the end goal of the Newkirk effect, but I think we're very close to that. And the whole idea is that we haven't ever been able to demonstrate that in front of a class. And I think we're right on the cusp of being able to do that with that larger diameter attachment, maybe even playing around some more with the smaller as well. And one of the things that I really liked that they did was to design, come up with a design that was flexible enough so that, you know, I can play with it, and then I can, if I need to, I could change to a different diameter and just cut different inserts. And you know, I think eventually we'll get to exactly what we're trying to get to. We probably could have gotten even closer had I been able to spend some time over at the school with them, but because of the limitations on the travel and whatnot, it wasn't possible. But that's okay. I'm looking forward to getting this in my hands next week and taking it the next step. So thank you.
Thank you. Other questions or comments for our group here? We have a couple minutes here left before we need to send the council into sequestration for their judging.
Yeah, I guess one last question I've got directed toward the team is, with everything that you've learned thus far, you know, and unless the curriculum has significantly changed since I was there about 10 years ago, a lot of this you probably had to learn on your own and wasn't quite what you learned in class. But knowing what you know now, what would you do differently if you could start the project over and you kind of had a clean slate?
I definitely think we would have jumped right on a bigger diameter rotor, or the pipe sleeve in general. We started off with that 10 millimeter attachment because we would have been thrilled if it would have worked on that actual smaller diameter since it's much cheaper. Additionally, we found that the pipe wasn't, when we actually purchased the pipe, it was hard to find one that was very concentric. And so we might have explored a few different options there to make it to where, like, for example, the pipe would be concentric or straight or not bowed, so that we could actually have an easier time to actually rub on it. As far as the vibration stuff is concerned, we don't get a whole lot of vibrations training here at Louisiana Tech, and so learning about it was very interesting. And I definitely think if we started over, we might do a little bit more digging to try to understand exactly the fundamental concepts a little earlier on, and it might have led us to a better solution towards the end.
Good, very, very impressive project overall, regardless, so thanks.
Thank you.
Okay, any other questions or comments for our team? Let me check the chat. All right, well, with that, I want to thank our team and thank all our judges and all you in the audience for attending our session. We are delighted to have you all on board. Please visit us again very soon at 5:15. If you go back to the program, you'll see a link there so you can learn more about the namesake of our conference. And there's going to be a bunch of people like that to thank. And then our judges will be providing me with the results of their top 2 finishers from this session. And you'll get to hear about the top 2 finishers of the other 2 sessions as well. So we look forward to having you all join us. Go back to that program, click on the award session link. We'll see you there at 5:15. Thank you all. Appreciate you tuning in.